So maybe we start.
Sure. Good morning, everybody. Welcome to the second year annual review of our ULI project. And my name is Shane. I'm going to be the moderator today. So our first speaker today will be Nara. And so Nara, the floor will be yours.
Thank you, Sheng, and welcome everyone to this second year annual review. We wish we could hold it again in person like we did last year, but this year it didn't work out for some logistics reasons. I'm happy just to get started and share the presentation that would summarize our second year. Please let me know if you will see the screen.
Yep, we can see the screen.
Okay, thank you so much. So welcome again, and let's get going. So NASA's vision for advanced air mobility aims to have a transformative impact for a few industries like emergency response, healthcare, by reducing significantly the travel time for mobility between urban areas and for cargo delivery, enabling delivery of small packages to big packages for different purposes. And yet, the scale of these operations makes it impossible to rely on human pilots, obviously. The complexity of operations makes it prohibitive, gives us prohibitive costs for pilot training, and obviously leads to the critical need for having autonomy with assured safety. I don't know why the GIFs are not running. This was supposed to be very impressive with GIFs, but it was running on the first slide, not here. Anyhow, let's move forward. Now slides are not going forward. So how to ensure we can have autonomous solutions with guaranteed safety? Looking into commercial aviation, starting from 1940s, having the pressurized cabins in 50s, air traffic control in 60s, fly-by-wire technologies, glass cockpits, safety management systems, GPS integration. All this led to our opportunity to fly 4.5 billion passengers this year with ensured safety, earning public trust. The industry has focused on safety with zero tolerance to accident policy, which has led to public trust. Learning from it, what can we do for the low altitude space? So the drones first appeared in early 2000, and then we see already the opportunity to deliver small packages with drones. Now we are talking about advanced air mobility as an industry on its own, where we envision people moving on so-called flying cars, on eVTOL aircraft between urban areas without running into major traffic issues. So how do we get to the same level of trust and safety what we have for commercial aviation? There are lots of things to be learned here and lots of things to be done. Yet the scope of this ULI is limited in a sense of its budget and duration. So we have identified a set of problems in perception, planning, and control that is enabled by the sensing technologies of today, the data and computation opportunities that we have. Again, we have a missing GIF on data. And the challenges that we're trying to address would be predictable performance in unstructured, uncertain, dynamic environments with verifiable and quantifiable operation. And we want to have competence awareness for contingency management. So we have identified 4 thrusts within this ULI project. The first one is the learning-enabled autonomy stack, where we bring in the control technologies, perception and planning technologies that are already proven through other projects, through our experience. That includes L1 adaptive control with distributionally robust adaptive control type of architectures, simplex for adaptive control with barrier functions, uncertainty-aware planning that comes with model predictive path integral control and Thalys variational invariance MPC, incorporation of barrier states, constrained covariance steering, and robust perception, which is robust to diverse semantic transformation, Shapley-based algorithm, pixel MPC. The technical challenge 2 involves the fast code level verification, where we plan to scale verification of heterogeneous mix of modules, learned and handwritten, where verification engine prototypes, optimized abstractions, incremental verification. We have runtime fault diagnosis and reachability analysis with technologies like discrete event and continued valued fault diagnosis, sample-based incipient faults, and reachability analysis in our thrust tree. And the last technical challenge involves testing, evaluation, and integration towards technology transfer. We have simulation environment development with photorealistic worldview. We have integration of systems and architectures through ROS. We have field testing and validation for Class G airspace. And we have algorithms for integration of this type of vehicles with these algorithms into the national airspace. However, everything that we described is not all-inclusive, and there are challenges beyond this ULI that are not addressed within our scope because of the budget, time duration, and the specific team that we have. For example, questions come up quite often. How can automation achieved through perception planning and control perform beyond human capabilities? We do not look into these issues. How do we address safety concerns a priori through systematic top-down approach? Again, this is also a scope outside this ULI. The reason I bring this up because these questions come up quite often in various meetings, and we have to understand that this project is limited to 3 years with the annual budget of $2 million with these 15 people on the team. Now I want to present the status for the second year of every technical challenge, while the individual PIs will go through details in their presentation. So the objective of this technical challenge 1 is to have autonomous stack with integrated perception, planning, control, and learning-enabled components. The significance of it is the learned information from the environment allows for safer decisions and operation in dynamic, uncertain environments, and the performance metrics is the mission success and safety violations that we have to watch out for. So the milestones for the second year were design of safe learning and exploration architecture. We have the L1 add-on module for robustifying, for example, reinforcement learning policies, DeepTune MPC for efficient parameter learning. We had integrated planning and control pipeline, covariance steering for VTOL planning and control for safe landing, software in the loop simulator for photorealistic rendering. We had development of machine learning model pruning algorithm, reconstructive neuron pruning for backdoor defense, fast model pruning for certifiably robust DNNs. And we had integrated perception planning and control pipeline where already we worked with different simulators to bring in these technologies to interact with each other. That included the air taxi, software in the loop simulator, bridging Guam with Carla. Guam is the generalized unmanned aerial vehicle simulator coming from NASA, and Carla is the photorealistic urban environment. So we have done lots of integration of different algorithms through these simulator environments that we're transferring these technologies to NASA. In technical challenge 2, where we look into fast data-driven and code level verification, we have objectives of hybrid tools for autonomy stack verification with code level uncertainties. The significance of it is the robust verification mechanism for early issue detection, and the performance metrics gets measured by the verification time and uncertain scenario coverage. And I will let already Sayan and Chuchu to go through the details of it in their presentation. Again, there was significant integration here with JAX Guam. There's the Guam version in Python and the RL-based controller, collaboration with other teams on JAX Guam. These integrations are important because this is what will bring us to the verification stage. We had a runtime fault diagnosis and reachability analysis for in-flight contingency management. And here, the objective is the advanced fault detection and reachable region estimation methods. The significance is the essential in-flight contingency management, and the performance metrics here we define through detecting and diagnosing the correct faults, runtime, and certified true reachable regions ratio. I will let Ali Karimodini and Melchior Ornik to go through these kind of milestones, what they have accomplished. Again, I want to emphasize that there was significant effort in integration of the methods through the Guam simulator provided by NASA. Finally, our last thrust focuses on testing, verification, and validation in real flights and through technology transfer to hardware platforms when possible. So we have tools and methodologies for robust and resilient autonomy framework testing and airspace integration, with the significance of realistic airspace testing of the development algorithm. And the performance metrics here for us is the software compatibility. I will let Petros and Christos talk about their progress of the year 2 as we are planning for the demos in May. And let me give a brief summary of what are the demos planned in May. Here we are significantly looking into integrated technologies. For example, together with Louis Shah and Bolli, we are planning on safe autonomy for air taxis with fault detection and collision avoidance. Right now, we are having testing in software in the loop simulators, full integration, and hardware tests are planned. For the second one, Evangelos is working with Christos on testing his covariance steering for vision-based safe landing, and they are integrating on the Mini Hawk VTOL platform of University of Nevada in Reno. And hopefully in May, we'll see some of this flight tests in Reno. Cyan is working on verification of conflict detection and avoidance in multi-agent scenarios. And we are integrating ACAS Q neural network with burst for more accurate reachability analysis. Integration with Mini-Hawk is planned again. Some of the other demos include the demos from the Thrust 3 from Ali Karimodini, where they are integrating prototype 1 for fault-triggered emergency landing maneuvers, and prototype 2 for reachability analysis integration. And Christos is testing this amphibious VTOL platform, what he's developing now with MPPI simulation-based testing and vision-based landing algorithms. So we're looking forward to seeing these flight tests in May. Our second year was also kind of celebrated with a number of papers, PhD students, graduate and undergraduate students, postdocs, and we had also some type of recognitions in terms of keynotes, additional grants in the area of safe autonomy. You see here the undergraduate class that San is teaching, outreach events, Girls in Aviation that Jessica is hosting at University of Nevada, Reno every year. This is a worldwide event with 30,000 girls in 31 different countries, just in the 2024 were recorded. UNR received a $36 million donation from Gilman Foundation for expanding its aerospace program in part because of the ULI. And saying NCAT received a diversity grant from John Deere, again related to UAV developments. We hosted a drone camp. In this picture, you see, in fact, me also in the middle school of girls in Urbana. So this is our team. We had change in Lockheed Martin because Chris Elliott departed the company. Now we have James Ramsey and Mike Nistroy replacing Chris Elliott. And you see the Illinois Autonomous and Connected Track. It's an ambitious project with $100 million investments promised from the state, where we'll have a facility for 3D mobility testing. And if we continue working on this ULI, get a continuation opportunity for it, we have the ideal environment for testing and maturing these technologies. This is our brief agenda of today and tomorrow. And Thursday will be the discussion day. All the questions can be summarized in chat. They will be made available by the end of each day for discussion. If no questions, we can maybe move forward and have Petros present the plans for the May demos. I can stop sharing.
Thank you, Nara. And we're going to have Petros give us a brief introduction about the demo plan in next May.
Yeah, just 1 minute to share my screen.
Sure. So a side note for everybody, we just noticed some bandwidth issue with our meeting. So if you're not speaking, may I kindly ask you to turn off your camera so that we can save some bandwidth for the presenter and the shared screen. Thank you.
So can you see my screen?
Yes, I can see it. It shows a website that did say download is in progress.
Oh, so in that case, I have some issue here. What do you need? This one? Okay. Probably now it's fine.
Yep, looks good.
Okay. So what I plan to talk about is some basic ideas about our third review in Reno, and some basic scenarios that we have we're working on to demonstrate. And so these are, I mean, Naira alluded to most of the things, so I'm not going to repeat what we are going to be doing, other than say, of course, that you know, the basic idea is to use the perception planning, the perception and planning and control developments from the other TCs, and trying to integrate that into some flight testing capabilities that we have, and demonstrate those using some of our platforms that we have developed at UNR, as well as at Sierra Nevada Corporation. So Christos, who has been the main person behind all these developments in the field testing arena, will give a lot of information and specifics about the platforms and the scenarios. And also Andy Smith from Sierra Nevada Corporation will be able to
thank you.
to someone be able to give us more details. All right. So we're going to be using different scales of aircraft. And first is the Mini Hawk that we have all seen. And that's something that was developed at UNR by the lab of Professor Papachristos. It has various capabilities. The point is that it is a small footprint. It has a small footprint, and we want to do evaluation of the developed learning-based autonomy components. The specifics, I will just leave them for Christos when his talk is on tomorrow. It's a small platform, and then another platform which is bigger in scale is this GANET platform, which is going to be used primarily for landing on water in an emergency situations, and it has a medium footprint, and we would like to use the capability to test edge emergency conditions that involve water-based landing. Again, details will follow in the talk of Christos. And finally, the last platform, which is going to be used, is SNC's Volley 10. It's really a full-scale unmanned aerial system, and it has a capability of carrying various payloads. It can fly quite long times, more like 1.5 hours. And as I said, it can carry a number of payloads. Andy will talk more about these capabilities. And we would like to do a commercial scale field evaluation of the developed algorithms and show capability for long-term in-flight stress testing. Now, the scenarios, you have seen quite a bit of some of that video here, but really the scenario using the Mini Hawk and Volley 10 would be to be able to handle an emergency landing in the case where we don't have any GPS or there's a degradation. So we're talking about a mapless operation, and we rely solely on onboard visual perception. So we would like to use these algorithms of deep learning to be able to, based on the terrain, to classify and the various options and be able to land autonomously and then do replan, because it has also capabilities of recharging and continue the mission. So that's one of the basic demonstrations that we would like to present. Now, next is again related to Mini Hawk, is the situation where we use this covariance steering based MPPI algorithm in order to cope with uncertainty during trying to, for example, to land, and then something bad happens, and we're trying to identify the unsafe situation and be able to create an alternative path to land the vehicle safely. And so this is a situation where we have simulations going on right now, and we're going to transition that to the to some real world experiment. And Mini Hawk would be the platform that we will be using. And so finally, there's this water emergency water landing using this other platform, the GANET, that was developed by Christos's group. And the case here is to show that we can land safely on a safely on water in case of an emergency, and also be able to then restart and move on after we charge. So in terms of the logistics and the general planning, as I mentioned, we're going to look at learning-driven emergency landing using the Mini Hawk and the Volley. So we're looking at using a test area that contains human-built terrain features like buildings or sports fields that can be identified by their appearance, and so in real time be classified on board from the vehicle. And then we would like to also be able to simulate faults And so the aircraft has to detect unsafe structures and and land to safe candidate zones. Again, there's mission replanning to approach based on visual guidance and safely land operation. We're going to use G-class airspace that we have been using in Nevada, and there's a particular areas that we have focused on that we're going to be doing this testing. And then for the last case, which is the amphibious field testing, there's another area that have been selected in the area of Silver Lake. And the point is to demonstrate mid-mission water landing, and both in vertical takeoff and fixed wing gliding mode. And we would like to do that repetitively. And again, using the area would be a G-class airspace. So these two areas that I'm talking about are about half an hour away from campus. And we are working now on the specifics on how we're going to have these demonstrations go during the final review in May. So we're still working again on the details. So we haven't fixed the particular days, but I will be working with Irene and everybody else. The available time windows for May are two: the beginning, May 1st to the 13th, and then after the Memorial Day, 28th to 31st. So we have to probably be able to pick a day during these windows. We're thinking of 2 days, one being devoted to flight testing, so visiting the sites and looking at the demonstrations, and then another second day doing presentations and discussions, which will take place at the UNR facilities. More details to come. Hopefully by the end of November, we will have everything, or the basics at least, decided on, and hopefully we can have everything demonstrated as promised. So that's pretty much all I have to say. Again, the details of the tests would be more analyzed by Christos and Andy in their corresponding talks. So that's all I have to say for my part.
Thank you, Petros. We have a quick question from chat. Maybe you can summarize it in a few sentences, and then we can switch to the next speaker.
Okay, so let me see, what's the question?
So it's a question from Kevin. He asked, does this include vision-based navigation over water?
I think that's right, and Christos can confirm that if he's available.
Yes, I am. Can you hear me?
Yeah.
Yep.
Yes. What kind of vision-based navigation are we talking about? So the goal here is to be able to do a regular mission and utilize vision as the mission's progressing, in order to be able to detect landing zones that can include potentially entire bodies of water, and then include those in the list of candidate landing locations, and then do safe landing on them, either through VTOL or through gliding-based landing on the water.
Thank you, Christos. For the sake of time, may I ask you to continue this conversation, if possible, in the chat, and then we'll have more time when you present, I think, tomorrow. So thank you, Petros, and thank you, Christos, for the presentation, the answers. We'll have next James from Lockheed Martin to present the latest flight test they had. So James, can you share your screen now? So I'm seeing your screen, and can you try to test the audio system from your side? Can you try to say a word or two?
Hello?
Hey, James, is that you?
No, it's Mike Nestroy. What James is going to get the charts up. So Mike Nestroy, in the room with me here in Fort Worth is Dr. James Ramsey and Dr. Aaron McInnes. They're the driving force behind our safe IRAD work this year. They took over when Chris Elliott and Josh Harris had left. So they are the guys who kind of shepherded the team. And James's presentation today is going to talk about our recent flight test on the X-62 Vista aircraft at Edwards Air Force Base Test Pilot School the first couple of weeks of September. So we are going to go ahead and start that presentation now. We're having some audio issues on our side, so we're resolving those. James,
Sorry, Mike.
whenever you're ready.
Sorry, Mike. I think there might be some echoing in the room. So can you double check your audio devices?
Yeah, we're double checking. Yeah, we're checking it now.
Okay, thanks.
I don't know. Need the speaker on your computer. Is it better now?
Still some echo. Maybe this is only me. Can anybody else confirm the hearing this echo?
Yes, I
yes,
am also
I-
hearing the echo. Yeah.
Okay.
Still echoing?
Can you
Yeah.
try that one more time? I think the echo seems gone.
Yeah, we're trying to move speakers and computers apart from each other.
Okay, I think it works better now. So maybe you guys can continue with this configuration.
Yeah, we'll do that. James will do his presentation right now
right.
for the sake of time.
Okay, thank you.
Can you see the screen okay?
Yes, we can see the slides being presented in the presenter mode. Thank you.
Okay.
Great.
Okay. Yes. So today we're going to give you an update on the safe flight testing that was performed on the X-62, a Vista aircraft. So just to give you a brief historical perspective, the SAFE program started with great talent and Dr. Chris Elliott and Josh Harris. They were the leads. I joined the team a year or two after that, and so since all three of these gentlemen have departed, the SAFE program has moved forward with Dr. Nestroy as the lead, myself, and Dr. Aaron McInnes. Okay, so the flight testing that we performed, we consider this to be stage one of our effort on our IRAD. The goal here internally is to bring in technologies, transition those onto LM products. The sort of concurrent goal as it pertains to the ULI is to give you a data point on the L1 technology and how it performs in a real-world scenario. So to do that, we looked at the L1 MP and WC just to distinguish this from MPC controls. This is modified piecewise constant augmentation. What we did was we looked at a simple NDI baseline control law that we hosted on Vista. And the idea was to bolt on this L1 control as an augmentation component, and then do a comparison between the baseline flight control and the augmented L1 control. So we kind of expected that we wouldn't see much difference for nominal behaviors. However, the goal was to see differences when there were actual failures on the aircraft in some way. So what you see here is just control architecture showing standard block diagram for us. So the regulator, the mixer, and the OBM represent the baseline control system. The mixer that we used, again, was very simple, so we did not use any control allocation or reallocation of surface effectiveness. So it was a very simple mixer, and the idea here again is to see how L1 would perform. And so in addition to the baseline here, we have the safe component, which was hosting the L1 control, and it augmented the commands coming from the baseline going into the mixer. So here is the sort of process that we took to go from, model and simulation all the way out to the actual flight test. So we started with a simple Simulink linear stitch model. That gave us really 5 flight conditions that we had available to us to tune for flight. And so the idea of stitching, of course, is you start with 5 and you kind of tie these things together to kind of create an envelope. For us, we actually just tuned one single flight condition of the 5, and that's what we flew, and we were able to actually move around the envelope quite well just with that one flight condition. So from there, going from Simulink to C code, that was sort of the next step, auto coding, and so that got us into sort of a coded 6-off environment that we have here. From there, we were able to go from that sort of software environment into an actual piloted dome simulation that we have, where we invited pilots to come in and actually fly the safe algorithm. From there, once we were satisfied with that, we then moved to bench testing on the real hardware out at Edwards. And of course, that then led to sort of the final stages of ground testing, where we loaded the OFP onto the vehicle and then ultimately moved into the actual flight test part of it. So what's coming up next is just some flight data, data that we could get cleared for this presentation. So it's going to be fairly short to keep us within this time frame.
Sorry to interrupt, James. We're still hearing the echoes, and I figure you were calling in through your phone. So is it possible that everybody in your meeting office mute their computer so that we don't hear the sound back from your phone? That could probably solve the echo problem.
Yeah, there's an issue with the computer that it won't mute the sound. So I think it's the computer that's defective here because we have it actually muted, but it.
Oh, that's the magic. The echoes are gone. Yeah, I think it works.
Okay. There we are.
Oh, wonderful. Thank you.
Okay. So here's a very nice photo of the actual flight test. What you see is Vista, and you see a T-38. And when I get to the flight results, we'll see we're actually using the T-38 for tracking tasks. Here, help. You bring his computer closer. Scared to touch it. I know. Like, yeah, we shouldn't touch it. Yeah. So what you see here is a setup maneuver. So it's called heat to guns. Base here represents that we're just running the baseline configuration with our NDI. No failures have been injected here. And so heat to guns is an acquisition and a tracking task. So first, the Vista pilot would first acquire the target T-38, and then after that, then he would attempt to track his movement. And so what we're looking at here is the pilot input, the commands, and the actual pitch rate tracking and associated with performing this maneuver and trying to follow this T-38. So on the left, it's safe off, so it's just baseline NDI. And then on the right side, it's safe on. And so we can see here that there isn't terribly much difference in the behavior between these two for the baseline, and that's what we kind of expected. Part of what we want to achieve here is that if the nominal system is doing well, then the safe or L1 algorithm should hardly do anything. And so this is the roll axis for that same heat to guns maneuver base, no failures. And so we can see that there is a mild improvement with safe over some of the bumps that we see on the left side with safe off, but nothing really to write home about. So now this next one is we then failed the right flap by locking it at 0 degrees deflection, so it is fixed there. And so we asked the pilots to again perform this acquisition and tracking task, heat to guns. We can see that in the pitch axis, we have very similar behavior in terms of error. In the roll channel, now, again, our mixer is not very smart, which is what we wanted to test here to see if the L1 can do compensation here. And so it does two things here. First, we see the bias correction that we get with it, but also if you look closely at the amplitudes of the corresponding peaks, you can see that the tracking of the overall dynamic tracking is improved too with L1 on. And so the pilot quoted on the left side that the roll, this rolling is really annoying. So he came back on the speaker with that, and he was satisfied when we turned safe on. So again, in the interest of time, I won't go through like all of the different cases. So this is kind of a summary of some of the other cases that we ran in addition to the base and the right flat lock. So what we see here, we're just looking at the mean absolute error over the time period in which we were performing the heat to guns maneuvers. And so the blue represents the NDI and the red is safe. And so we can see that overall, in general, safe performs with less mean error than the baseline NDI system, and it's really pronounced certainly in the roll axis, as we saw in the previous plot. But this gives us, let me just mention, so the rudder case here is a case where we degraded the rudder effectiveness by, we allowed the rudder to have 75% of its effectiveness, and I think we may have run another case where we did 50%. But in looking at that particular case, we can see that the SAFE algorithm certainly gave us better regulated error. For the OBM case, that represents a shift in the CG. So we looked at what happens if we shift the CG a bit and don't inform the control system that said shift has occurred. We can see that there isn't too much difference there. The baseline system did pretty well, but again, in the roll axis, there's a little better tracking, again, with L1 safe active. Another set of metrics that we wanted to look at was pilot workload. So since we had a pilot in the loop, one question is, when we have safe on, does it decrease the pilot's workload, or does the pilot have to be more aggressive on the stick in order to kind of get the response that he wants? So we wanted to look at these two metrics. So aggressiveness is defined by this equation that you see here, the integral equation, and it's mainly just what percentage of the max stick force is being used by the pilot. For duty cycle, it's more of a time metric. What percent of the time is the pilot moving the stick over the course of the test? And so, when you're tracking, certainly you're going to move it more, but relatively speaking, if you're able to track well, that's going to decrease some of that duty cycle. So when we took data for one of the F-16 pilots, so we looked at his kind of stick workload. So when you're looking at this, there are a couple of things to point out. So red is the NDI, blue is the SAFE algorithm. The dashed lines that connect common shapes it's really highlighting the fact that it's the same flight test that we're looking at. And so you can go down the list here. You can see X is the OBM CG shift. The diamond is the right flat failure. The circle is the rudder control surface degraded control effectiveness, and the base is the plus. So what you want to see here, if we're talking about reducing the duty cycle, then you want things to move to the left on the x-axis, and you want things to move down on the y-axis when we're talking about aggressiveness in terms of just being required to move the stick more because it's more difficult to control the aircraft. So in this case, when we look at blue, the fact that blues tend to be to the left of the reds and shifted down relative to the reds indicates that SAFE is performing a bit better than the baseline NDI, and in some cases, a lot better. So in summary, again, the idea was to evaluate the L1 MPC in actual flight testing. So we've done this on small-scale aircraft, and so this was an important test for us because it's now full-scale. Again, we wanted to look at a simple baseline, host a simple NDI baseline controller and determine the extent to which the L1 SAFE would give us improvement. So what we saw is that, again, if we did not have failures, we noticed that there wasn't much improvement because there wasn't much need for improvement in some of the cases, but where there was, you could see you could get some deltas in terms of tracking. We saw that. But certainly when we injected failures, if the baseline was not able to arrest those. The L1 did a good job of actually bringing things back to, good performance and good stability. So just to mention, for stability here, there were no stability issues noticed in flight. So it certainly, there was no issue with, degraded stability with L1 in the loop. These are, I'm showing the failures that we did do. So the CG bias, the right flap, the reduced rudder effectiveness. The fourth one we planned to do, and we actually tested that in the dome sim, and it looked really great, and we were really happy. But when we made it out to the aircraft, we found out that they changed the configuration of the Vista aircraft to limit the amount of differential elevator that you could have. And that was, I'm told, to protect the aircraft in terms of twisting and braking. But by doing that, that prevented us from actually doing this elevator lock because we would have expected the unfailed elevator to move certainly beyond their limit for differential elevators. So we had to scrap that last second, but that would have been another, I think, important data point for us to actually see in flight. And again, based on what we saw in the dome sim, that would have been another successful test. Okay, so from there, the most substantial improvement, certainly we saw that in the roll axis. And from this, we'll be moving into the next phase of safe maturation on LM platforms. That concludes my talk here.
Thank you, James. I think there are a bunch of questions from the chat. So for the questions and from the audience, feel free to open up your mic and we can have this conversation to do the Q&A.
Yeah, in the absence of anyone else, I'll go first. I had two questions in there, but it really boils down to the simplified mixing. Obviously, things worked really well in roll, and it was beneficial in pitch, but less so. And since the two primary failures were the rudder effectiveness and then also one of the flaps. My question on the pitch was, in the F-16, typically differential elevators is a huge roll driver and then also pitch. So I'm just curious if the less impact noticed in pitch was primarily due to the failures that were initiated weren't really using, that actuator, the failed actuator. I don't know what the general mixing schedule is. That's all.
Yeah, I think we certainly would have seen more, had we, been able to actually lock the rudder, certainly.
Lock the tail, you mean?
Yeah, the tail, I'm sorry. Yeah, lock the elevator.
Yeah, because in the dome sim, we saw a dramatic improvement when we had them coming into Fort Worth to fly at the dome sim. They basically sometimes didn't even notice that one of the elevators was locked at zero in our simulation here, which is why we were excited to try to test that. But you're right, it is the primary pitch effector, right? So we wouldn't expect to see a lot change in pitch because both elevators are working all the time. And then, of course, I guess you pointed out, I think there's a blending ratio between flaperon and differential tail of like 2 to 1, or 3 to 1 or 4 to 1, something like that. And once you lock one of them, then the differential tail has to basically make up the difference, right? So you see more of a difference between left and right horizontal tails during those maneuvers.
Okay. All right. Yeah, I was just wondering if that was the primary explanation for the difference in pitch and roll, and I guess the answer is yes.
Yeah, yes, absolutely.
Okay, thanks.
So what was done in the yaw axis?
The rudder effectiveness was reduced by 25%.
So let's see, you only presented data for pitch and roll. Did you do all three axes in the flight control?
Yes. We did.
And-
So for the rudder one, when we looked at that data, there wasn't like a huge difference. There was, if you integrate that over time, there were spots where certainly it was better, but it wasn't as overwhelming as like in the roll axis.
So when we do fine tracking tasks, gross acquisition and fine tracking, I think that's what you're calling the guns part, where the pilots typically move the pipper from wingtip to wingtip. Did you do that kind of testing? Or I couldn't tell from looking at body rates what was actually done.
There was no sweeping of the actual pipper itself. It was just an attempt to keep the pip on target as close as they could to the 50 millimeter diameter.
Okay, thank you.
Any other questions from the audience? If no more questions, then the next activity on our agenda today is actually a short break. So everybody feel free to relax a little bit, and we will resume at 10:15, where Nara will give the updates from TC1. So thank you. Welcome back, everybody. So as planned, we're going to resume our review with the presentation by Nara. So Nara, if you're here, can you share your screen?
Sure, let me just share it.
Okay.
And you suggested to shut down the video for the bandwidth. Let me do that.
Okay, appreciate that.
Okay. So welcome to Technical Challenge 1 or Thrust 1, where we'll talk about the safe autonomy with verifiable data-driven control development. As the Lockheed Martin flight test showed, so we have this L1 adaptive controller that we developed over the past 20 years and have flown and tested on NASA subscale commercial jet, Learjet, and the Vista F-16. Our flights were back in 2016, and now the Vista has been modified. Within this ULI, we have grown to augment that L1 adaptive controller with risk-aware path planning, robust perception, real-time autocode verification, fault detection, all these thrusts that we mentioned. But Technical Challenge 1 is about perception, planning, and control. And the way it relates to other thrusts, you see here the signs. So we aim to achieve code level verification, reachability analysis, testing. And let me go ahead and say what has been particularly developed within this thrust, upon which I will switch to our particular work. So Evangelos, Bolli, Luisa will cover methods from robust perception and risk-aware planning. We will talk more about safe learning and adaptive control with some work in the planning area as well. The history of L1 adaptive control is summarized here with its implementations on the platforms that I just mentioned. Now, as we move towards safe learning and verification and validation, we consider these more challenging environments as a benchmark. Actually, this environment was brought to my attention by Evangelos back in 2018 when I was visiting Georgia Tech for a seminar. He asked me if we could fly L1 here. And it was clear that if flying the Learjet or Vista F-16, we had the flight envelope defined and we were just doing robust augmentation for the types of failures that we just saw, like actuator failures or other types of failures. In this environment, the reference trajectory, the path continuously changes, and we need continuous learning, updating the reference trajectories, and so on. Basically, it necessitates new types of solutions and new types of guarantees, and we came up with this framework of distributionally robust adaptive control. How to be robust to errors in distributions. Again, my GIFs are not working, these beautiful GIFs. I don't know, they all worked before starting this meeting this morning, and maybe the bandwidth is just not enough when we have 50 people joining it. We did all the tests this morning. So the way this distributional robust adaptive control work, which is funded by AFOSR, relates to this NASA ULI, is that we are trying to ensure, for example, robustness to data shifts. As during the operation, the data continuously changes and it may not be aligned with the data for which the training has taken place. One of the examples would be the reinforcement learning type of approaches that have become quite popular. And we can try to augment L1 adaptive controller on the top of these architectures under certain constraints and assumptions to show how we can improve in case the system faces new type of data that has not been used during the training. So why is this important? So the data-driven control synthesis is today very popular, actually. You go to conferences and this is what you see all around. Reinforcement learning is one type of data from this, one type of control method from these methodologies of data-driven synthesis methodologies. And model-based reinforcement learning works the following way. So it's sequential, it takes data, builds the dynamics model, and there is optimal control synthesis via certainty equivalence principle. Empirically, it's well performing, but it has poor robustness against uncertainties, errors that have no errors, learning errors, data quality, distribution shifts. So the performance can be deteriorated. How to improve this performance? So L1 adaptive control could be augmented as a remedy for these situations. What are the challenges? So the challenges of using robust adaptive controller with model-based reinforcement learning algorithms boil down to the fact that reinforcement learning algorithms learn models that are highly nonlinear. Parameters do not coincide with the true parameters of the physical system. Nominal models produced by these algorithms are not amenable to control tools. One possible solution is to constrain the model structure to the control affine or linear class, and this would come at the price of sacrificing the performance. So the conventional approaches attempt to do model affinization, right? So they are limited to trained model that's control affine, or they explicitly disturb the baseline algorithm, which is non-generalizable. So what are the requirements? If we want to add an L1 adaptive controller, the design requirement is that the high-level algorithm design cannot be changed. So we don't touch the baseline. This was also the case with the Vista flight test that we just saw. And no additional requirements from the high-level MBRL algorithm can be made. The framework has to integrate MBRL with L1 adaptive controller, while L1 operates on the need of affinizing the learned dynamics, and affinization will happen along the control trajectory. So L1 gets implemented on this affine dynamics. How do we do this affinization? So we just use first order Taylor series expansion, which is only a good approximation around the U bar, the trim condition. And we update this U bar according to some switching law with the threshold, dropping all the mathematical details. Here are the results where we have done tests over 5 benchmarks used in reinforcement learning literature. That's inverted pendulum, swimmer, hopper, walker, and half cheetah. The baseline MBRL algorithm is Metro RPO. And the L1 augmentation, as you see, outperforms in all the scenarios except for one, and this is most likely because either we did not tune enough, given the deadlines. There is a single L1 adaptive controller applied across all these 5 platforms without any retuning. So one case could be an outlier, saying that either there was a need for more tuning or considering a better models. Again, my apologies for the GIFs not working, then it makes more impressive. So how it can be applied to this ULI? So if we extend the usage of AM for safe control and flight of VTOL vehicles, I'm sure you'll see already around lots of these reinforcement learning approaches being applied to VTOL models. And if we integrate the framework with Guam, we can basically show how L1 can compensate for errors due to the data shifts that were not used in the training scenarios. This year we have no opportunity to do poster sessions, but this is not the only work where we have contributed to this ULI. As I said, this distributionally robust adaptive control framework, which is significant theoretical development, supported by our AFOSR grant, can be directly applied, for example, for augmentation of reinforcement learning, tested in Guam scenario. While here we have some other papers from students that if we had a poster session opportunity, we could have done posters on this. And I want just simply to make sure that all the students get acknowledged for their work. Let's go one by one. So this is a work that we did jointly with Ilya Kalmanovsky for handling state constraints and input constraints. Ilya has this method of reference governors. And he asked if we could augment it with L1 adaptive controller, where the transients could be improved with the L1 and the constraint handling could be more efficient. So given the scope of this ULI being applicable to urban air vehicles that would operate in urban areas, consideration of constraints is critically important. So challenges in constraint control under uncertainties. So the model uncertainties will prevent accurate prediction of system behavior, which makes it hard to enforce the constraints. Some of the approaches that are known in the literature, like robust or adaptive approaches, have their own limitations. And what we did, we designed an L1 adaptive controller for uncertainty compensation, deriving the explicit transient bounds, and then we tightened the constraints with these performance bounds, and then designed the reference governor for the nominal system with tightened constraints. This is what we worked on with Ilya, and the paper was published as a full paper in Transactions on Automatic Control. So there is reduced conservativeness in constraint enforcement and enhanced tracking performance through inherent uncertainty compensation mechanism. And there is computational efficiency achieved, and the demonstration was done on some flight control examples in the paper. Proto-MPC would have been another poster from another student. It's an encoder prototype decoder approach for quadrotor control in challenging winds. So what is the background here? Data-augmented models are increasingly recognized for representing dynamic uncertainties in different vehicles, including these VTOL vehicles. And the challenges of using data-augmented model-based controllers in multitask setting include a single offline trained model is highly task-dependent with limited generalization capabilities, and using multiple task-specific models proves inefficient and requires switching loss to maintain stability. Existing approaches include some of these online learning methods that construct a new model using streaming data, balancing between exploration and exploitation, and control-oriented meta-learning approaches that involve complex control filtering design that are system-specific. So the Proto-MPC is an efficient online task adaptation. It is multitask meta-learning method that effectively balances shared and distinctive representations across different training tasks. It has efficient and rapid task adaptation using online streaming data, and we demonstrated it on quadrotors in our lab, and we can extend it to the Guam model as well. DiffTune MPC. This would have been another poster. The DiffTune paper got accepted in Transactions on Robotics, and its version for MPC is in Robotics and Automation Letters. So MPC has seen significantly growing applications in aerial vehicles, as we all know, including VTOL vehicles for advanced air mobility platforms. There are challenges here with parameter tuning that include the high dimensionality of the parameter space, nonlinear relationship between parameters, and the existing approaches come with either inefficient methods that come from sampling-based parameter tuning or differential programming-based parameter learning that formulates as an open-loop learning problem, unable to learn practically meaningful parameters. So DiffTune MPC gave us a framework for safe and efficient parameter learning. Efficiency is achieved through differentiable programming, which facilitates finding optimal parameters via gradient descent. Safety is derived from constraining the parameters within a safe set, and we emphasize the closed-loop parameter learning with a focus on systems performance. And we have featured the open source code for rapid deployment through our GitHub repositories. We also work on kind of new hardware development. This OmniDrone is an overactuated platform, and we enjoy playing with it because it gives us a new level of agility in terms of flight. Its maneuverability due to the decoupling of the translational and rotational motions gives us a significant advantage to surpass the traditional coplanar multirotors motion capabilities, and it enables new applications in advanced air mobility, especially when we want to do aerial manipulation. The challenge is that the existing methods that did not account for rotor dynamics were resulting in poor performance. What we have here done, we have included the rotor dynamics as a part of the model and designed a controller, a new type of geometric controller with global exponential stability proofs that accounts for rotor dynamics instead of treating it as unmodeled dynamics and being robust to it, but taking the rotor dynamics into consideration, we are achieving significant tracking performance like you see here in these pictures. Now a little bit about the planning methods. Those were the control papers. So this is an optimization-based planner with B-spline parameterized continuous time reference signals. So this work is motivated by the fact of moving in cluttered environments where we need rapid change of the reference commands and the trajectories, we get significant computational overload. So the existing approaches like optimization-based planning offer precision, but they are computationally intensive. Sampling-based planning methods are efficient, but lack necessary precision in dense environments. So this B-spline parameterized optimization-based planner has low computational load. It enables real-time planning, decoupling optimization dimensionality from discretization resolution. This is the key point. It generates smooth continuous signals, provides agile responsive maneuvers in dynamic environments, and enables high-frequency planning. We were able to test it on this car of our center of autonomy. It's a self-driving car, and on the right you see the blue, that's the obtained new planner as compared to the green planner, which was coming with the baseline discretization methods. And finally, this is the work that was done directly on the Guam as a vertical takeoff and landing vehicle, so reference command optimization for transition flight mode. So traditional vehicle designs are not well suited for AAM. Lift plus cruise vehicles designed to address the shortcoming of traditional vehicles, capable of vertical takeoffs and landing while leveraging the efficiency of fixed-wing forward flight. The challenge here, though, is how to craft unique and fuel-economic trajectories and actuator references for VTOL vehicles. Here also we have done some work, and this is really very close collaboration with the NASA Langley team, jointly developed with them. So this optimization-based approach that we have developed for designing this reference command focuses on encouraging sparsity of rotor and pusher thrust. So simulation validation demonstrates advantages over the traditional differential flatness-based approaches, and it can be extended to 3D dimensional lift plus cruise vehicles and validated within Guam, offering more thrust-efficient flight and sufficient authority for contingency management. As you see here, the elevator deflection that has to be limited to 30 degrees was reaching almost 81, and with our new approach, we were able to maintain it within the 30-degree limits. Now a little bit about the demonstrations within this thrust one. So as a thrust on perception, planning, and control, we will support many of the demonstrations that we discussed. So one of these demonstrations is what Evangelos will summarize in his presentation, and maybe Christos will talk further. That would be the vision-based safe landing using covariance steering coming from Evangelos. And the second demo that we will be also heavily involved would be safe autonomy for air taxis with fault detection and collision avoidance that Luisha and Bolli are developing. This will be tested in software-in-the-loop simulators, and we have plans for integration and hardware tests as well. Whether we will catch up with May, I'm not sure, but the software-in-the-loop will be done for sure. The first test is definitely planned for a real-world demo. And we'll support all the TCs, like I said, with perception, path planning, and control algorithms, including this fault detection and collision avoidance that we will do with also Sayan Mitra and other co-PIs of our team, and also the reachability analysis that we do with Ali, Yanis, and Melchior. These are the list of publications, and I believe I'm on time even maybe to take one or two questions, so we lump the questions towards the end. This concludes my presentation.
Thank you, Nara, for the wonderful presentation. Now, any questions from the audience for Nara?
So Naira, let me ask you this for those who may not be particularly familiar with reinforcement learning and why it might be so popular. Can you give a sense of what reinforcement learning would bring to the problem of autonomy, especially in congested urban area environment and okay, so its relevance?
Right. So reinforcement learning is a data-driven approach. I mean, the beauty of it is that you avoid all your wind tunnels, heavy modeling efforts, and you can kind of do control design by using data. And but when you go to new environments that the data has not been observed, so its performance will be deteriorated. And this is where we can use the L1 adaptive control to augment it. So basically, it's an approach that comes from computer science community, machine learning people. It's another way of doing optimal control with data-driven methods. And the models get constructed from data instead of the wind tunnel. So it can speed up your baseline design, but it will perform poorly in new environments. There are, of course, methods to robustify this reinforcement learning, again, coming from computer science community, domain randomization, all these other tricks. But when we do it with L1, we have all these performance guarantees and predictable performance.
I'd like to also add that it's very, very nice that L1 is used to tighten the constraints while it provides safety. And then, of course, you can use data. There's an echo. I don't know why. Anyway, I just wanted to point out that this combination, and of course then using data in a new environment also helps. But L1 can help a lot in getting rid of the irrelevant information, if you will, the transient and so forth, so that the constraints can be placed in a less conservative way. And I think that's a very good point, a big plus. So that's all. That's what I see here.
Lena, can you elaborate a little bit on what you mean by getting rid of the extraneous information? You're talking about constraining the exploration space?
Yes, Erin. Hi, Erin.
Hi.
Yeah, I think the L1 can help sort of like level the playing field quite a bit from irrelevant or extraneous, as you put it. And then, of course, you have a much easier terrain to grapple with, to set up the constraints. And of course, if you're in a new environment, it's a different ball game. You still have to use data, but again, you use this combination to make things easier and faster for you. So.
Hi, Naira. I'm not sure if we're having time for another question.
Sorry, Yanis, I'm afraid we don't. At this
worries.
stage, we have to keep it moving. And we have a dedicated discussion session after we're done with the presentations today. And as I'm speaking, Sion is preparing to set up his slides. So Sion, whenever you're ready, you can go. Go ahead.
Okay. Hi, everyone. Good morning. So I'm going to give you overview of one part of Thrust 2, which is on verification. So you can see my screen now, right? Okay.
Yes, Sion, we can see it.
Yeah. Okay. So Thrust 2 has two branches. One focuses on code level verification and work on this particular tool that my presentation will focus on, called Verse. And there has been several integrations with the Guam model and other parts of this ULI project. And then later on, you'll hear from Chuchu Fan about the second branch of Thrust 2, which is about propagating this reachability densities. Okay. All right, so let me say something about Verse. You saw this part of this presentation last year, but I just wanted to remind you what this tool is about. A large number of students and collaborators have contributed to this tool. Verse is a Python library for describing and verifying multi-agent autonomous scenarios. For example, detect and avoid protocols, air traffic management protocols, planning scenarios, and so forth. You can download it and run it from this URL given by the QR code. The design philosophy behind Verse is as follows. First of all, we think code is math, so there is no need to learn new specialized languages or formalisms to use Verse. You can describe interesting algorithms, differential equations, all of that just in Python. So at this point, most engineers and undergraduate students are learning to code in Python, so that's all you need to describe these systems. So underlying our systems are going to be some form of hybrid automata, and you would want to talk about correctness properties of these hybrid automata like safety and liveness and so forth. Again, no need to really learn about special logical languages for specifying those. You can just state them as assertions in Python. And the third one is low code. So even if you're writing code in Python, things can become really large and complicated, but we have paid some attention to making the Verse system modular and portable. So one scenario can be ported to a different scenario with a few changes in line of code by just say altering the map on which you're running the scenario. Okay. And then I want to summarize the highlights of our accomplishments for year 2 before we dive into the details. We have made some advances in the core architecture of this tool. There are new data structures and algorithms that improve performance. This is work mainly led by Alex Wan, but also Yang Li is the main developer of Verse. He's online to answer more questions. There has been integration of Verse with several case studies that are of interest to this project. There's one case study I'll mention on applying Verse to analyze air traffic management or collision avoidance protocols, ACAS-XU, together with this Guam model that you've heard about. This work is ongoing. I don't have final results, but we're starting to get some interesting results, and I'll tell you where things are. This is led by John Bullock. And there's a second case study about collision avoidance with trajectory predictions. This was done by Daniel Zhuang through an internship at NASA, summer internship. And the third highlight for this year has been this user study where undergraduate students are using Verse in a class with actually more than 70, close to 90 students, which is sort of a new thing. Formal verification tools are typically not used in undergraduate classes. So we are conducting this user study, and I think we'll learn something interesting from doing this. Okay. So let me just remind you what Verse looks like. Here is a scenario. Again, we talked about this last time where drone is trying to avoid a collision with another drone, and there is some logic that it uses. So this is a simple collision avoidance protocol. So what you would write in Verse looks like this, which is very similar to what a Python description of the system looks like. It hides certain things like the actual dynamics of the drone, which is in a separate file. But then there is this assert, which talks about the safety property that you care about. Okay. All right. And then if you create such a scenario, you can say, okay, I want a scenario with such and such tracks and so many drones. And then finally, you can either simulate the scenario by invoking this function, or you can verify the scenario as well. And verification would lead to computation of this reachable set, from which then you can ascertain the safety of the scenario. If you wanted to run the same scenario on a different map, let's say it's not a parallel lines, but a figure of 8 pattern that the drones are doing, you would just change one line of the code to run the same scenario on a different map, and you would get reachability analysis on that map, right? So this is what I mean when I say low code. So the user does not have to write a lot of code to try different and interesting new scenarios. It sort of has all the benefits of a modern programming language like modularity, object-orientedness, and so forth. Now, internally, what Verse is doing is it is constructing this reachability tree. So it's exploring the uncertainty in the continuous state of the system, as well as all the uncertainties arising from the discrete uncertainties. So for example, the branches in the decision logic, the drone could be flying up or down to avoid the obstacle. And there could be many such branches that arise combinatorially. So internally, the tool is exploring all those branches. And we have made extensive use of this Ray framework. This is a modern machine learning framework used for large-scale parallelization of tasks. And because we are using Ray, we get the benefits of massively parallel computation and speed-ups of up to 6x in some of the examples that we have tried. Okay, so now about the new stuff that's happened this year, of which there are 3 things. So the first thing I mentioned is that there are some new data structures that we have implemented in Verse. This is a lot of work. So the first implementation of Verse used these axis-aligned rectangles to represent uncertainty in this state space, for example. Now we are using what are called these generalized star sets. It's a fairly recent data structure to represent uncertainty. So here's a picture of a star set on the right-hand side compared to a rectangle. It can be more general than this trapezoid that you see here. So a star set is represented by 3 parameters. There's a center, x0. There is a set of basis vectors, v, and then there's a predicate, p. And the set is defined by this formula here. So it's all the points such that they are described by the center plus some combination of the basis vectors, where the coefficients of these basis vectors satisfy certain predicates. Okay, so those are the 3 parameters. So immediately you can see that if you want to describe a linear combination or a convex combination of the basis vectors, that would be like a linearity predicate that you would assert over here with P, and that would give you polytopes or zonotopes. But in general, star sets can be more expressive than those. So star sets generalize polytopes, zonotopes, and other things, and this makes the reachability analysis in Verse much more precise than just using hyperrectangles. Now, there is a second innovation that has gone into describing, or I should say, implementing these star sets in Verse. So, for example, in representing this set shown by this blue blob over here, you can see that there is, of course, this big rectangle that you could use to approximate it, or there are a couple of different star sets, zonotopes in this case, that could also over-approximate the blue blob, right? So there are different possible over-approximations. So what we are doing is actually we are optimizing the choice of these parameters in describing the uncertainty in an optimal way, where optimal means minimizing the volume of the set, right? So we choose the center based on simulations, and we optimize the choice of the basis vectors. So in this case, we would get the purple parallelogram to get an optimal representation of the uncertainty in the analysis. And this figure sort of shows you what happens over a longer time horizon. These parallelotopes can rotate to align themselves for more accurate representation of the reachable set. Yes, so so this optimization is happening using machine learning, and there's a loss function that we have designed. This is not yet published. We are going to submit. We are looking forward to submitting a paper based on this work later this year. Okay, so now there are 2 integration case studies we have done. The first one is applying Verse to this detect and avoid kind of problem where there is an ownership which is trying to avoid an intruder for which we have a predicted trajectory. And this work was done by Daniel Zhuang during his summer internship at NASA, and then he interacted closely with the developers of Verse throughout to make this happen. So the ownership in this example is a simple Dubin's type aircraft model. The intruder is available to the ownership's logic as a prediction trajectory. So it's not just the current position of the intruder, but we are getting a prediction of the trajectory described by some sort of a spline plus some uncertainty around it. So this required us to modify the Verse architecture a little bit, because now we have to deal with the sensor on the ownership, which is not just giving us the sensing of the current state of the world, but it's giving us a prediction, right? So the decision logic and the sensor has to work with not just states, but time sampled predicted trajectories as well. So that required some engineering, and with that, then we can do analysis like this, which looks at different avoidance trajectories, like the red ones. You see the branching structure there again, which are the 3 different avoidance trajectories for the ownership based on the predicted trajectory of the intruder. And you can do this for multiple intruders as well. So there are 2 intruders in this second picture, the light blue and the dark blue. And we are able to... Sorry. I think Christos, your microphone is on. Yeah. So, and you can analyze these scenarios with multiple intruders to figure out which collision avoidance strategy is effective in this urban air vehicles scenario. All right, so the second case study is in a similar vein. So this is also a collision avoidance protocol. It's a well-studied protocol called ACRL-UIUC. There is a neural network representation of this protocol that has been looked at by various other researchers. And so what we would like to do here is analyze this Guam model running ACRL-UIUC as the collision avoidance protocol. So that gives you a closed loop system. And we want to figure out from what kind of initial conditions we can verify the correctness of the system. Now, this also is not a straightforward application of Verse. We have done some prior work with the Guam model, but this ACRL-UIUC protocol is a neural network. And there is no straightforward way to plug in a neural network as a decision logic in Verse. So what John Bullock has been looking at, again, in collaboration with our team, is how can you create an abstraction of the neural network as a decision tree, which can then be plugged in to Verse. So that's what's going on there. So you see this diagram at the lower right corner, which is giving us a slice of the decision logic implemented in the neural network. So the different colored zones are different parts of the state space of the relative position of the ownership and the intruders. So there are distances and angles in that state space. It's 5-dimensional, really. You are seeing a slice here. And then depending on the different relative positions, there are different advisories that the ACRL-UIUC protocol gives out. So it can be like climb up or make a hard right turn and so forth, right? So the colors represent different advisories. And so that advisory then goes into the decision logic and closes the loop with the dynamics of the Guam model, right? So here what we are showing you is the approximation of the neural network decision logic above, and the decision tree that has been constructed to approximate the neural network, right? And once we have a decision tree that is accurate enough, we can plug that into Verse to do the end-to-end reachability analysis. So this is ongoing work, and I think it's also an interesting methodology for getting a neural network or complicated models of decision logics and then creating a decision tree out of that, which can then be analyzed in a closed loop setting with complicated dynamics like the Guam model. So again, this is ongoing work, and we'll hopefully have a paper submitted sometime early next year. Okay, so those are the two integration studies. I'm going to finish my part of the presentation with the other interesting thing that has been going on. So we did a user study for Verse. So we want to ultimately study how designers and engineers use formal verification tools. What are the bottlenecks? Why or why not use these tools, where these tools are effective, where do they get in the way, and so forth, right? We don't have access to engineers and designers. Trying to interrupt their work and do a user study with them doesn't seem feasible. So we do the next best thing, which is user study with future engineers. These are the undergraduate students in our classrooms. So I teach a class on autonomy, safe autonomy, with now about 90 plus students every semester. So one of the assignments in that class, it has like 6 assignments once every 2 weeks. One of the assignments in that class is to design an autonomous system, like a simple logic for autonomous emergency braking in a car, okay? And so what we are doing is we are introducing Verse as an analysis tool for the logic that they have designed, and then evaluating the experience of the students through surveys. So this class is pretty diverse. So as you can see here from this pie chart, there are mainly ECE and CS students, but there are some mechanical engineers, there are aerospace engineers, some master's students, very small number of PhD students, so mostly undergraduates. And so what they are given are 2 design tasks, and it's about braking in different kinds of environments with pedestrians and traffic lights and different kinds of initial conditions with different speeds. And so, for example, one of the scenarios is the car can sense a traffic light at a certain distance. It's also going at certain speed, not a unique speed, but a range of speed. And there's some initial uncertainty about the position of the car. And then it has to decide whether it should slow down and stop, or whether it can speed up and actually go through the intersection without violating the traffic laws, right? So there's a little bit of a decision to be made there. And then they can write down the decision logic in Python, and they can either call Verse to do verification using reachability analysis, or they can just simulate, right? So these are 2 different maybe ways to provide evidence for correctness of their design. So they're solving 2 problems in 2 different methods, and then the survey is designed carefully to evaluate comparatively how they see these 2 different methods. Okay, so this is done in collaboration with my colleague here at Illinois, Katie Driggs-Campbell, whose expertise is in human-computer and human-robot interaction. So she knows how to do these user studies and what kind of metrics and survey design techniques have to be done. Yeah, so this is a reachability diagram for this this collision avoidance with pedestrian. You can see computed by Verse. So the key metrics we look at is the system usability scale score. This is a standard metric people use for different computer tools. And we compare the students' preferences for reachability verification versus simple simulation and testing. So the initial findings are okay. So the students actually preferred testing over reachability for the initial design. But they also saw the value of reachability in providing stronger evidence for safety. And we learned a lot from these surveys about where there are the bottlenecks for the usability of the tools. and where we need to improve usability to get more buy-in from this population of users. So for example, the speed, scalability is pretty important, right? Sometimes these verification runs would go on for 10 minutes, and that's too long for the students. There are simple improvements in documentation, I think, that would also help. And currently, we are not reporting counterexamples found by the tool in any usable way. So that could be another big improvement that we can look at. Okay, so I think I'm mostly out of time. So again, the takeaway from this part is this tool. And I've had many interesting conversations with other Thrust leads and ULI team members about how we could use Verse for other parts of this project. Some of these things are ongoing. The big improvements this year is this new data structure and algorithm for star sets, the integration case studies that are progressing well with both Guam and this prediction-based collision avoidance, and then this user study that we will continue to do in the future semesters. And again, we hope to write sort of one of the maybe unique papers that does user study with formal verification tools. Okay. And yes, there is also ongoing work on applying Verse to help with onboard planning. We have had several meetings and discussions with Christos, Petros, and their side of the team as well. Yeah. Okay, so I'll stop here and take a quick question or so if there are any.
Thank you, Sayang. Irene and Kevin, if you have questions, you can ask Sayang now.
Go ahead, Kevin.
Let's see, so my comment there was just about if you have to approximate the neural network component you're trying to V and V, that destroys the whole premise of V and Ving that component.
Yeah, that's fair. Yes, so if you're running the neural network on the onboard aircraft itself, then yes, what we are verifying is different from what is running. The ACAS-XU protocol itself, my understanding is actually came as a set of rules first. And then some folks created this neural network approximation of those rules so that it was used as a compression mechanism to begin with, right? So whether we want to verify the rules, the original rules, or the neural network for this particular example, yeah, I don't know. We are trying to develop a methodology for verifying this collision avoidance protocol, and as long as we can sort of capture most of the state space, how the neural network works and the rules work, I think we would be exercising the methodology in the right way. It's not going to be a hard claim that, yes, we have actually verified the Guam with the neural network.
Yeah, thank you.
Sorry,
Sayang.
Irene, I know you have one question.
Yeah, we don't have
but
time.
That's so here's a side note. So we decided to use the short breaks as a free discussion time, as if we're in person, so that people can chat. And that's a good time for questions and answers. So we'll defer the questions we don't have time to answer to that session, and we'll put a kind note to the chat. So with that, thank you, Sayang. And next we have Louis. So is Louis here? Okay, Louis not here. So in that case, Ayush, postdoc working with Professor Louis Shah, will present on behalf of Louis. So Ayush, you have the screen set up, and go ahead.
Good morning, everyone. My name is Ayush. I'm a postdoc working with Professor Louis Shah. And this is our research on certifiably safe and robust perception for learning-enabled autonomous systems, including air taxis. The big challenge that this research addresses is a challenge that is recognized by many people in the research industry. Deep learning solutions form a necessary component of the autonomy solutions for autonomous air taxis and even ground vehicles. However, these deep learning solutions have this pattern where as you increase the training dataset size, their fault rate reduces. But there's an unavoidable long tail of faults. This happens because machine learning inherently uses probabilistic model to approximate deterministic logic. On an implementation perspective, the sheer explosion of parameters in these solutions makes any kind of a formal proof or code coverage extremely difficult, if not impossible. So we think we need to tackle this problem and attack it from both ends. First, we need to improve the machine learning itself to reduce the fault rate. But the second thing, which is the focus of our research, is to create system designs that can mitigate the safety impacts of critical faults that will inevitably occur in these machine learning solutions. The inspiration for the solution comes from Control Simplex, which is one of the seminal works from Professor Shah. In Control Simplex, as a very simplified example, there's a high reliability, albeit low performance safety controller that is able to completely override and overtake a more complex but unreliable controller if that more complex controller is leading the system to an unsafe state. So the question is, can we apply the same logic end-to-end to the whole system while still somehow dealing with the fact that, unlike Control Simplex, we no longer have the ability to replicate all the functionality of the more complex machine learning enabled autonomy layer, because as I stated previously, some tasks do require deep learning solutions and there are no good alternatives for them. So how can we achieve some level of this redundancy by trying to create this verifiable safety layer, which only uses fully verifiable and analyzable software, which can be certified for its behaviors? On a practical note, this machine learning layer has a lot of functionalities that are needed to support autonomous vehicles, both ground and air, which means there are many fault types that need to be considered, which is impractical for us to deal with all at a time. So we chose one of them. Based on real world data, we find out that obstacle detection faults are the most important kind of faults for these autonomous systems. So we focused on creating a solution for these kind of faults first. To that end, we created this verifiable obstacle detection, and we have discussed this earlier in this group, so I'll very quickly summarize this. Using LiDAR-based obstacle detection geometric algorithm, we created a deterministic model for its limitations and capabilities. Using this deterministic model, we can do now this. We can compare the output of this verifiable obstacle detection within its operational design domain defined by the deterministic model. And within this domain, we can see whether the perception system in the ML layer has an obstacle existence detection fault. But the existence of a fault is not enough to justify an override. We also take the trajectory input from this ML layer and determine whether the fault causing obstacle has a potential to collide with our vehicle. So when a fault exists and it has a potential to threaten the safety of our system, the safety layer intervenes and applies the control and overrides the control of the ML layer. We have, in the past year, published this work for both air taxis and ground vehicles. Specifically in air taxis, we have integrated L1 adaptive control and did a close integration between our action override block and this L1 adaptive control. So specifically, in a landing scenario for an air taxi, which can have obstacles beneath it, if you're trying to avoid collisions by decelerating the air taxi and making it stop before the obstacle, the key control parameter that determines our ability to do that is the max deceleration that the aircraft can support. We can assume the static worst case, which is we take the absolute worst case for all parameters, including the disturbances in the air. On the other hand, with a close integration with the control system, we can do an estimated observed worst case, which means that if we take the observed disturbances, the estimated max disturbances from the controller itself, and use that to estimate and observe the real-time estimated worst case for the max deceleration. The good thing is, L1 adaptive control already computes this term on estimated disturbance, and therefore we don't even need to change the controller at all to get this value. Putting this instantaneous max deceleration through a time window, we get a dynamically confirmed estimate on the worst case deceleration value. We did this evaluation on a simulation setup that I'll discuss in a short while. On the left side, we have the static worst case. On the right side, we have the, apologies, let me quickly get a laser pointer. On the right side, we have the dynamically confirmed value, which on average was roughly 3 times higher. We start the air taxi at a 100-meter position, and we have an obstacle in its path. Using the model from the verifiable obstacle detection and the rest of the system, we can predetermine these limits for Vmax safe using a deterministic logic, which says that as long as the vehicle descent velocity does not exceed this velocity magnitude, then we are able to decelerate and avoid the obstacle. And we find in the simulation results that that is indeed the case. In both cases, we are able to avoid the obstacle. As you see, we are able to reach the obstacle much faster with the dynamic conformation. So if the obstacle was not there, we would have landed 1.5 times in a 1.5 times shorter duration. And that's the value of doing the dynamic conformation with the control. While this work is published for ground and air vehicles, there are several limitations. The key one is, as we discussed in the starting, we focused precisely on one type of fault, and we need to expand that to be able to cover other kind of critical faults in these systems. For that fault itself, and because of the limited capabilities of the safety layer as yet, the operational design domain of the safety layer is constrained, and expansion of that is one of our future goals. We do not have any pathfinding capabilities within the safety layer yet, which means that when the system gets stalled behind an obstacle, manual intervention may be required to recover from that, which of course is not ideal when we're talking about air taxis. So we have a couple of ongoing works which alleviate some of these limitations. The overall architecture change that we are now looking at is called synergistic simplex, or we are calling it synergistic simplex, and it tries to create a cooperative synergistic interaction between the verifiable components and the ML layer components. Let me take an example of that with cooperative actions. So a cooperative action is where the safety layer is able to leverage ML layer capabilities to do a best effort to maintain the operation of the system even in face of failures, while still ensuring that the prior deterministic fail-safe behavior from persistent simplex is not disturbed at all. So we maintain the fail-safe deterministic behavior, and adding a probabilistic fail operational behavior to that using this cooperative actions. As an example from ground vehicles, let's say there's an obstacle in front of the vehicle that the ML layer is unable to detect because of a machine learning fault, but the safety layer, the obstacle is within the safety layer design domain, and therefore it's able to detect it. In that case, the safety layer obstacle detection will then communicate this to the ML layer planner, whose output will be then used to try to evade this obstacle. We evaluated this for over 271 different scenarios from the new plan dataset for ground vehicles, and we find that in 17% of the cases, there's still an override initiated by the safety layer. In perception simplex, this number would have been 100%. In 57% of the cases, we still end up stopped behind the obstacle. However, this time the stop was guided by the ML layer planner, which means that it can consider performance metrics like passenger comfort that the safety layer would not. Finally, the key fail operational behavior is this 26% of the cases where we can pass this particular obstacle. This evaluation was admittedly done for ground vehicles, and as our simulation setup for air taxis is developing and reaching a state where we can do this evaluation there, we will do that shortly. Another ongoing work is a close collaboration with Professor Boli's group to add a safe lander, which is an extension of their safe auto and safe driver solution, which was recently done for ground vehicles. The safe lander will provide us the ability to comprehend and track in real time complex safety goals and specifications that are in human readable language, but then they can be then comprehended and tracked in real time. I believe Professor Boli will talk more about the specific solution. And now I invite Simon to talk about his solution on robust object recognition.
Hi, everyone. I hope I'm audible. Can everybody hear me?
Yes.
Cool. Yeah. So, yeah, if you can go to the next slide. So, yeah, before I get into the details of the architecture, I'd like to first talk about the Council of Development Assurance Levels, or DALs, which kind of highlights the danger of kind of mixing assurance and performance elements in a safety critical system. Essentially, what we don't want to do is to have a lot of things to fail at once. Therefore, so kind of inspired by this philosophy behind DALs, we devised the following assurance levels for our synergistic and perception simplest pipeline. Essentially, what we have here is first we have level 1A, which kind of dictates the risk of crashing and collision, where anything in the vicinity of the aircraft should be avoided at all cost. Then on top of level 1A, we have level 1B, which is responsible for having the aircraft obey any applicable regulations without compromising level 1A. For example, the aircraft perhaps needs to actually land in a correctly assigned landing area, not, for example, in the middle of the runway. Lastly, you have level 2, which is kind of intended for the aircraft to achieve its mission objectives, the original mission objectives, whatever it is. For example, it could be taking off, or to just simply go somewhere, or to land. Yeah. So if you could go to the next slide. So using the specified DALs, the entire philosophy behind the design of our synergistic and perception simplest pipeline is the clear separation of the safety and performance components, and is to use the simplicity of the safety components to guard the complexity of the performance components, as illustrated here by this more detailed diagram here. Next slide, please. So in this diagram, we have the architecture that adheres to the concept of DAL by having a two-layer design. Such separation dictates that the high assurance layer, or the HAL, is only responsible for robust and reliable object detection, corresponding to level 1A capabilities. That is to say, we don't want to crash, and we would like to detect anything in our vicinity reliably. Since it's not necessarily a requirement for us to recognize anything in the surrounding to avoid crash or collision, that's by having HAL focus solely on object detection kind of simplifies its design and its complexity. The HPL, on the other hand, focuses on robust object recognition, providing us with necessary knowledge and information and the capabilities needed for level 1B, and for us to not violate any regulations or rules. The decision module here serves as an interface between the HAL and HPL for any subsequent downstream modules, such as planners or controllers, to provide reliable level 2 mission capabilities. So finally, we're currently also working on a hardware-software evaluation platform called Biped that fits everything together into like a single tangible end-to-end pipeline. Next slide, please. So in this instantiation of synergistic and perception simplex design, in HAL, we have the first component, which is the verifiable absolute detection introduced by Ayush just now using depth-based point cloud segmentation techniques. The second component in the HAL then takes the segmented regions and combine them into a cluster of fewer but larger regions called collision avoidance zones, as regions we should never attempt to pass through. The collision avoidance zones are organized based on their individual criticality and are passed to the HPL as prioritized object detection results. In the HPL, we first have a set of software frameworks that enable us to rapidly annotate any applicable data sets with visual attributes. Those labeled visual attributes are then used to train our neurosymbolic recognition pipeline that first employs deep learning to predict the visual attributes, and then uses computational graphical models such as probabilistic circuits or PC to probabilistically compose the visual attribute predictions into the final prediction that we want. The neurosymbolic pipeline is robust by itself to distribution shifts, such that's further increasing the reliability of the overall pipeline just all on its own. Aside from robustness, we're also working on a method to tackle the challenges of interpretability of the pipeline. So by replacing half of the originally end-to-end black box prediction pipeline with analyzable probabilistic models such as the PC, we're able to build interpretability framework that allows us to attempt to explain any mistakes made by the pipeline with counterfactual explanations. For example, the interpretability framework is able to, for example, give us something like, oh, the pipeline would have given us the correct prediction if it predicted this particular visual attribute correctly instead of incorrectly, or the pipeline did what it did because it predicted these visual attributes. Such level of analyzability and ability to backtrace into the middle of the recognition pipeline is non-existent in the current end-to-end black box solutions. It's also worth noting that many of the above components right now shown here are currently work in progress, and I also skip some of the specifics due to interest of time. It's also worth noting that the biped evaluation platform is currently a ground platform. Our plan is to first perform our early experiments quickly on the ground platform as a stepping stone. We have devised subsequent plans to retrofit this ground platform into an air-based platform for any later UAM-related experiments. Next slide, please. So yeah, as shown here, our plan is to have a progressive transition from ground-based platform to the air-based platforms. We plan to first perform our integration components and test them quickly and rapidly on with some early experiments on this ground-based platform as a stepping stone, and then we can progressively then move on to retrofitting the system into increasingly more advanced and progressively risky, more risky air-based platforms. So the final stage of this transition is the Mini-Hawk, which supporting both simulation and in the real world. Next slide, please. So the biped ground chassis here that we have so far is a two-wheel system. So it's quite similar to a flying taxi in terms of their naturally unstable physical nature. So the current ground-based platform also comes with sensor suite normally found on autonomous air taxis, such as camera, LiDAR, whatever equipped it on board. All data produced by the onboard sensor can be transmitted to a remote host and accessed using our biped ground station software developed here, shown on the left. Next slide, please. So we have designed the current hardware, the hardware platform to be modular, such that the motherboard of biped is actually detachable, so we can simply unplug it from the current two-wheel ground-based chassis and just simply plug it into the sensors and actuators on any air-based chassis. For example, here, such as this Quanser helicopter system we have in the lab. So this particular air-based chassis, we can place it in the lab above like a mock landing zone area with the sensors facing downward towards the ground. So we can use it to simulate a vertical landing scenario in this lab environment with various factors, real world factors. So we can then place various objects around the landing area to simulate ground vehicles, obstacles, and personnel. And then we can use the biped firmware and the ground station software we develop to automate a data collection process by controlling this helicopter chassis to loiter around the landing area and to use the camera and LiDAR to collect any relevant data that we can later use to train our pipeline models. Yeah, that's essentially what I have on my end here. So going back to Ayush.
Thank you, Simon. So in addition to these physical platforms, to make sure that our research solutions work in the real world and not just simulation, we are also continuing development on a simulation setup in a photorealistic environment to ensure that we can test out all kind of crazy, unsafe situations that we can't do on real platforms. To that end, we have been developing this simulation software based on ground vehicle as the physical vehicle and car simulation. In the recent months, we have made the whole solution setup very easy to use and highly scalable by essentially creating a microservices-based architecture using Docker containers, ROS, and a unified hierarchical config. So as the baseline simulation looks something like this, thanks to Hyunjin, we have now the correct model for the landing pad in the vehicle. So we want to change it. We just change a couple of values in the config file, run the simulation. It takes a couple of seconds to start up. And now we'll see that the initial position of the vehicle has changed. So it's now doing a sideways landing. We can also use the same config files to add obstacles in the path of the vehicle or around the vehicle. We can choose the model of these obstacles. We can go as crazy as we need to be to set up the exact scenario. And as you'll notice near the end of this particular snip, we also have a mini hawk vehicle coming into the view. Obstacles can be said to have motion and predetermined paths. And finally, of course, we can do a mix and match of static and moving obstacles. In all the previous videos shown were using the JAX-GOM vehicle as the backend for the vehicle physics. But we can also now support mini-hawk vehicle thanks to Mikhail from Professor Naira's group. And that integration is now somewhat complete. So it is definitely supported, but there are some manual steps involved that we are now trying to eliminate. You can also collect safety metrics, for example, if collisions happens or if the landing velocity meets certain safety thresholds. The whole process is highly automated now with a single command. It builds, runs, and as a proof of concept for that, I have been trying to train an RL reinforcement learning based flying agent. While the agent itself has not converged, we could reach tens and thousands of episodes for the learning without any manual intervention, which means the overall system is stable and automated. We also have a ground station now. The repository for it is already accessible by multiple ULI members, and we'll be making it public shortly. The big next step for the simulation setup is first to set up end-to-end autonomy, and the owners for specific tasks are listed here. We are also integrating our research solutions for the May 25 demo, as we discussed earlier. And finally, we are still trying to expand the simulator capabilities more to create, to be able to support more complex scenarios. And Duo from Professor Naira's group has been a very effective communicator for bringing people to us who might be able to use the simulation, and we are working with them to set up to their particular use case. Finally, to summarize the overall presentation, the big challenge we are dealing with is the inevitability of faults in learning-based solutions. And in presence of these faults, how can we still safely use learning-based solutions in safety-critical systems like autonomous air taxis? Our solution is to use verifiable solutions to mitigate the safety impact of these machine learning faults and also improve upon this behavior by using synergistic integration between these components. During the demo, with at minimum using the simulation setup and also hopefully using the physical setup, we showcase that despite AI hallucinations, the faults do not have a safety impact on these systems. We have already published the proof of concept of the system via analysis and simulation and tackled the most critical type of fault, which is the obstacle existence detection fault. Our milestones before the demo itself are completing the synergistic integration of ML and verifiable components by early next year, and then validation on the physical platforms by March of next year. These are all the collaborators across our projects with various different technical expertise, and I'm thankful to all of them for all of their contribution towards this work. Thank you so much for listening to this presentation, and please feel free to ask any questions.
Thank you, Ayush and Simon, for this wonderful presentation. Now, any questions from the audience?
Hello, Ayush. I have a question.
Yes,
did you have a chance to test this sensor from multi-vehicle using Kala already? I think that this should work, right? At this moment, I guess you are just using some trajectory to move these vehicles in the air, but you are not getting the sensors coming from those vehicles yet, right?
Absolutely. And this is why we are actually waiting for you and your contribution towards the end-to-end autonomy setup. And once that is ready, with the path planner that Chuyan is working on, and also a reachability analysis that Yang Li is working on, once all of these components are in, we should be able to do end-to-end autonomy. But right now, you're absolutely right. We have the initial position, the final landing target defined. The initial position is defined via the configuration file. The final position or the landing target is defined communicated via the ground station in real time to the vehicle. And just by these two parameters, we are doing a simple control loop to reach the final position. There is no sensor or collision avoidance in there. Separate to this.
Yeah, but I think that it's going to work anyway, because the color demonstration for autonomous car, they already have multi-car simulation that has been used. So I think that it should work. Nice
Absolutely.
video. Thank you very much. Yes.
Absolutely. We do believe that it should be, with these components in, it should very well be possible to do this end-to-end autonomy. And that is our goal here, to have an end-to-end autonomy system which can provide the baseline above which now everybody can start doing their improvements to it.
Good. Thank you.
That's good timing. So thank you, Ayush, and thank you, Hyunjin, for the question. Next, we have Evangelos. So I hope Evangelos is here.
Yep.
Okay,
I'm
sounds
here.
good. You can share your screen.
Yes. Okay. Can you see my screen?
Yes, we can see this PDF presented on your screen.
Okay. And there is no echo.
No echo.
Okay, thank you. All right. Thank you, everybody. My name is Evangelos
Control L, go into slideshow mode. It's showing.
Okay, let me see.
Control L, Evangelos.
Okay. I have a Mac actually.
For a PDF, you should just be able to say view full screen, but.
Okay, let me do it. Stop sharing. How about if I do it like this? How about like this?
Good.
You made it.
Okay, thank you. All right. So I'm going to present the work that we did last year, the second year for the ULI, and I would like to start from the feedback that we received the last year and present how we try to address some of these points, not all of them, but we try to address most of them. And so the first, I think, important question that came up in the discussion that we had last year is whether or not we can certify trajectory optimization. That's a comment that was made by Kevin, a question that was posed by Kevin, and there was also discussion to feasibility. There was another comment actually that was in the written review feedback to us. I think that was by Richard on like whether or not we can use some interesting use cases of generative AI for emergency landing trajectories. So I have these 2 points here because I think these 2 points are actually, I will show you that they are actually related. And then there was this overall feedback that we received in terms of integration, right? Like what that we should work on efforts that put together demos and integrate planning, perception, and control. And so in this presentation, actually, this is the outline. So the first thing I'm going to do is I'm going to try to address the question by Kevin. The second part is to see whether or not I can address the question by Richard, and then show the work that we did towards integration for the last year. And then I would like to highlight a few works that we also did, and they are relevant to this project. And some of this actually used, and it's part of submitted papers. Okay, so let's go back to this question of whether or not we can certify trajectory optimization, right? And I think that's you know that's a uncomfortable question. It's a difficult question to ask to answer, and so we try not to avoid it and kind of try to face it. And so the proposal that I have is that the solution to this question is a technology that's called deep unfolding, and it's something that has been used in other areas of science and engineering, primarily in the context of compressed sensing and image processing. So deep unfolding, what it does is actually to bring the connection between iterative optimization and deep learning. And so what it offers is it really provides a functional representation of optimization algorithms. So if you do not understand or you don't remember anything else from this, like from my presentation, I think that's the only point that, or perhaps the most important point that I would like to make in this presentation. Because once you have an iterative optimization algorithm and you can find a way to represent it in a functional form, then you can ask all of these questions about verification and certifiability, right? So what is really deep unfolding? You can get any optimization algorithm, which typically has this iterative form. And what you do is actually you can unfold it. You can say, I'm going to write this algorithm down up to for a specific number of iterations, all right? Let's say in this particular case, we have n iterations. So this algorithm can be a QP solver, it can be a iterative QP solver, any optimization algorithm that has this particular form is an algorithm that you can unfold. And then what you can do is you can take the parameters that appear in every iteration of this unfolded architecture and essentially treat these parameters as learnable parameters. So the idea is as follows. I can use the initial iterative optimization method to generate thousands of millions of examples, which will give me the x1 and the xn plus 1. The x1 is the initialization, the xn plus 1 is the solution of the trajectory optimizer. And then using this unfolded architecture, I can essentially use this set as a training set to fit the unfolded architecture to the solutions of the iterative optimization methods. So the iterative optimization method can take thousands of iterations. The unfolded architecture can be 20, 30, 40, 50 iterations. It doesn't have to be, you don't have to have many layers here. So we can think of every layer as every iteration as a layer. And the promise is that now, if I can show that I can learn this architecture, if I can provide generalization bounds, and if I can show with very few iterations, I can outperform the iterative optimization counterparts, then I'm in business, right? Because now I have a functional representation of trajectory optimization. And so we will start with large-scale QP problems. These are essentially problems that appear in many solvers, right? In sequential quadratic programming, linear quadratic programming, differentiable dynamic programming. And then what we will do here is we are going to in the case where this optimization problem is very large, we can actually decouple it, and we can do a very standard trick that we will do in distributed optimization. That's not necessary if the optimization problem is small, but if the optimization problem is large, then these decoupling architectures work very well. Okay, I think I messed up a little bit. Okay. Right. Great. I apologize for this. In effect, resolve. Okay, So we have this large-scale optimization problem, which appears in many solvers. We can decouple it. This is a standard technique by introducing this W tilde, which is a consensus variable, and there's a little bit more work to do to make this constraint optimization problems to be easily solved. And so if I were to take these problems and represent it in a Lagrangian formulation, I will end up having okay, I will end up having a augmented Lagrangian method that is basically I have an objective function. In this objective function L, I have all of my constraints. I have the Lagrange multipliers, and now I can essentially solve this problem, which I have taken from being an unconstrained problem to a constrained problem. I can solve it in essentially 3 steps, all right? So this is in step 1, we are going to optimize for X and Z. In step 2, we're going to optimize for the consensus variables. And in step 3, we're going to optimize for the Lagrange multipliers. And so now what we're going to do is we are going to unfold this optimization method, and we are going to treat parameters that are essential, tuning parameters that are essential for the optimizer. We are going to represent them as trainable parameters, okay? So in this particular case, we pick the rho, the mu, and the alpha to be the trainable parameters. So then, okay. So then if I were to demonstrate this in an unfolded way, this is how it's going to show up, right? Like we have these 3 layers where we have the updates for the X variable, which is essentially the trajectory. We have the local updates for the consensus variables, which we use to handle the constraints. And then we have the dual updates for the Lagrange multipliers. And this is just one layer, right, of this deep unfolded architecture. So now if I have 10 iterations, or if I have k iterations, I will have k layers. And so now let's see how this actually thing works, right? So here what I'm showing is a number of examples in which we have this deep unfolded QP architecture, which I'm going to use for from testing into random QPs to random network QPs to couple to optimal control of coupled pendulums, to optimal control of coupled oscillating masses, network flow problems, and then there is a problem in machine learning which is called distributed lasso. So notice here that while we use the iterative optimization counterparts, we use hundreds of iterations to generate data with which we can use this data to train the deep unfolded QP. The deep unfolded QP is outperforming within 20 iterations, is able to actually reduce the optimality gap, right? So that's something that essentially goes outside of anything that I have ever seen when it comes down to working with a QP optimizer. And so not only that, now if we want to talk about, now that we have a deep neural network architecture, we can essentially now talk about generalization bounds, right? How well this architecture generalizes. Again, this is an architecture that solves optimal control problems that are translated to quadratic programming problems, constrained quadratic programming problems. And then again, we have a theoretical loss. There's an empirical loss. There is this P is a probability distribution over the parameters of the Len optimizer, and this P0 is the prior. This is a typical back-based bound. which we can actually compute. And again, what we can see is that within 20 iterations, the deep unfolded architecture can reach that bound, right? That generalization bound, while the iterative optimization counterparts, it will take hundreds of iterations to be able to come close to the deep unfolded architecture. And so let's go back to the question, right? Like the question was, can we certify trajectory optimization? And I think this is to answer these questions. This question, there are two steps, at least two steps. The first step is essentially to see if there's any way that we can get a functional representation of any trajectory optimization method, right? And the answer to that is yes, there is a way to do it. It's called deep unfolding, right? Once you have this representation, you really care about how to train it and then how well it actually generalizes. And then the benefits of this is that you have an interpretable representation, right? You have a neural network representation that comes from optimization. It's scalable and very fast. It has better performance than the iterative optimization counterparts. It has generalization guarantees, and it is optimization dependent. And so now what we want to do this third year is, now that we have a way to represent trajectory optimizations in a functional form, we want to be able to see how we can verify them. We want to be able to actually understand the input-output relationship, right? And that's basically what we want to do in the third year. So I think that we were not able to fully address Kevin's comment, but we were able to make a significant step forward. I want to say that there is no work on deep unfolding that has to do with optimal control. A lot of the work was done in the area of compressing. The reason is because there are very few people essentially who build optimization methods for trajectory optimization. Many people will actually work with solvers. And so to have a deep unfolded architecture, you have to have a method that generates the data to train the underlying architecture. Now, the second question was like, okay, can you guys use generative AI to find emergency lighting trajectories? I think this is related because we can think of these deep unfolded architectures as foundational models, right? If somebody was asking you, what is a foundation model for optimization? My answer to this question will be a foundation model to optimization is this deep unfolded architectures. Now, how we can use that within a generative AI framework, this is something that we did not really have time to think about. But this is definitely in our radar for the last year. So then in terms of integration, I think we actually focus on essentially creating capabilities to do a lot of perception experiments, right? Like gathering experiments in urban environments with actual visual data is a challenging task and poses many safety risks. So what we try to do is to essentially build a software that allows us to get real-world images, and then from these images we can create an environment within which we can fly in simulation and train our perceptual models. And so here is so then here is one example that we were just very recently were able to have it ready. Is essentially the building that our lab is the CODA building at Georgia Tech with images taken from a satellite, and then this is a covariant steering task where we try to land the in drone on top of the CODA building. This again, the same task here. And then also in terms of hardware, we work very closely with ONR. One of the first tasks that we did was to identify a state space model for the Mini Hawk. We try to help them to modify their autonomy stack so that we can use optimization-based control, and then incorporate not only the dynamics of the mini-hod, but also the dynamics of the Guam on these simulated environments that we have. This software that we built that takes actual images from actual environments and creates a simulator, a photorealistic simulator. So then a few other highlights very quickly. There's always the need to do adaptation. The way how we think about adaptation is within the context of differential optimization. You have an architecture that has multiple layers and you want to be able to tune them. A lot of these layers are optimization modules, and there's a question of how you can pass gradients through optimization module. The way how we do that is with not with div tune. The way how we do it is by using the implicit value theorem, which allows you to find these gradients explicitly. And there's a paper that was published in RSS. There's a theoretical also analysis in terms of the errors, how the errors that you make in computing these gradients through the implicit value theorem, how they affect the performance of the system. And then I don't think I have time to talk about these videos, but we try to demonstrate this on a small robot in the GT Robotarium lab. Another task that we did was to work on covariance steering algorithms. A lot of these algorithms up to this point have been formulated as semi-definite programming optimization problems. And typically these optimizers essentially treat the problem as a single layer, as a single optimization. And what happens is that very often you don't have really feasibility. And so what we did was to try to reformulate this optimization problem so that we can relax them. And so the way how we do that is as follows. So we have this stochastic dynamics for which we have mean and variance. There are change constraints that have to do with obstacles, and so we want to be able to avoid these obstacles, and then we have distributional constraints that have to do with initial distribution and a target distribution, right? And so there's a cost function, and then there's a policy that has a open loop and a feedback control, and we are optimizing for both of them. And so the way how we came up about dealing with this issue of feasibility is essentially using the operator splitting trick that is used in distributed optimization in methods like alternate direction method of multipliers, or ADMM for short. So we want to control the mean and the variance. So what we will do here is that we will create copy variables. One set of copy variables for mean and variance will deal with a steering problem. The other set of copy variables for the mean and the variance will deal with a change constraint satisfaction. And so then when you do optimization in the first block, you do optimization for these two different sets of copy variables, and there is a second block that tries to achieve consensus, essentially tries to make these copy variables to agree. So what this allows us to do is during optimization, the optimizer can violate the constraints, but at optimization, when it has reached the consensus, the constraints are satisfied. And these are just some of the results that we have, and also I've also shown that on one of our previous videos. So the conclusion here is that there is lower cost, there is high level of safety with this new formulation for covariance steering optimal control, but the optimizer is slower, right? And so the last part is that there's a lot of work that has been done in the last years on comics optimization, and I think that work has really paid off, and we have seen a lot of recent results from industry. But how much of this technology actually scales or is applicable to the cases where you have vehicles that they have to operate in dense environments. That's an open question. Typically, when you have obstacles, this is essentially translated to a non-convex trajectory optimization problem. You have multiple local minima, and you have to be able to pick the best one. And so how we can handle with these sources of non-convexities that come from the task and not necessarily from the dynamics. I will actually argue that non-convexities that come from the dynamics are easy to deal with. And so 8 years ago, we thought that, like MPPI is a way to go, but I think since then we made a lot of progress. MPPI has many issues. And so this is the idea that we proposed this last year, is essentially a hybrid scheme where you really try to bring gradient-based optimization and sampling-based optimization within one framework. So the idea is as follows: if you have a landscape that is non-convex because you have essentially two local minima, then what you do is you have states where you follow some number of gradient descent steps, and then once every few iterations of gradient descent steps, you disrupt the gradient descent process and you sample around the solution of gradient descent the way and if you find that there's a better solution, then you pick that better solution, and again you go through that process of following gradient descent steps. So this is an alternate process, and the way how you sample actually plays a important role, and this is where a lot of this is to achieve this. Theoretically, you need to be able to regularize your optimizer with an entropy regularization method, right? But one thing I want to say is that this idea actually is something that we find out in other spaces. There's this very interesting book that I would like to recommend, especially for people who are in the higher ups of companies in terms of how one can improve decision making. And so I just want to show this these last two slides. The first row is essentially all type of NPPI algorithms that we have used, and one of them is actually what is deployed in the DARPA Racer project. Almost all teams in the DARPA Racer project use NPPI, and they trust it. So we have set up these environments actually to show that even a stochastic optimization method can get stuck to local minima very easily, while if you follow these methods that have this hybrid scheme where you have you alternate between gradient descent steps and sampling, then you can essentially avoid this local minima and find these global optimal solutions. And so this is something that we would like to deploy on an actual vehicle. And there's a lot of work to be done here in terms of the theoretical aspects of optimization, right? Like how often you disrupt, how many gradient steps you need. Can you prove the asymptotic convergence of the optimizer? And can you come up with a actually more advanced analysis that gives you finite time convergence? So these are some of the questions that I'm not sure how much time we will have for the third year to do, but I think that the future of MPC and trajectory optimization methods is actually within this context of hybrid techniques between gradient descent and sampling-based optimization.
Sorry, Evangelos. Yeah, made it in time. So I'm not sure if we have any time for Q&A after your session, since we're already in the small break period. But as we just discussed, we can use this time for those who are interested in the works presented in this morning as, a unofficial discussion session. Well, everybody can take their break. If you have any interest in talking to any one of the PIs or co-PIs here, you can stay and ask the question. So we'll have this break and resume. Thank you, Duo, for that visual presentation. So we'll resume here at 12:05, and we'll continue with Professor Bo for her presentation. So thank you all, and see you shortly. So it's 12:05, and we're going to get back to our agenda to continue the review. And may I ask if Bo is here?
Yes, I'm here.
Okay, awesome. Will you share your screen and start your presentation from there?
Okay, yeah, thank you. Thank you, everyone. Let
All right,
me
thank
share
you.
my screen. Yeah. Okay. Okay. Yeah, thank you, everyone. It's a great pleasure and honor to share some of our recent progresses for ULI project here. And today I'll mainly talk about part of our recent progresses on the risk assessment, safety enhancement guardrails for autonomous vehicles and in the air. So first of all, as we all know that of course, machine learning AI is everywhere and including different like a single modality, multimodality, and like robotics and agentic systems, etc. But of course, we know lots of vulnerabilities, including different like say safety issues that we know and reported by autonomous driving vehicles and say if we use chatbot or multimodal models to build such agentic systems and robotics, there are different potential consequences and safety concerns as well now. So that we can see indeed it's very challenging to build the so-called safe and secure like AI systems we have aimed here. And therefore different AI regulations and like policies have been coming out to ensure that we can build safe and secure trustworthy AI infrastructure and platforms. But even with all these regulations, it's not enough yet because from the technology side, we have not been able to provide very rigorous formal guarantees and certifications for safety and security yet, right? Therefore, today in the report here, I want to discuss a little bit progresses from our group towards this goal in terms of providing safe, secure, and trustworthy certifications for autonomous driving vehicles and air, so that we can see how we can like make more progresses later on as well. So first of all, I want to give a quick example of, say, we use like driving vehicles as an example to see how we can generate very challenging safety critical scenarios, which draw on the long tail distribution of real world, say, driving scenarios, such that we can perform red teaming, penetration testing, and provide stress testing for vehicles and robotics. For example, here, this is one example that how we generate the challenging scenarios like this. So basically, this is a very interesting example that we can leverage the current advances of foundation models to flexibly generate very diverse and challenging scenarios. In this figure, we use vehicle as an example, but we can also use other, say, some like air flight landing scenarios that we have tested as example. Okay, sorry. So, for example, I haven't finished this slides yet. So for example, here, what we do is that as an input, we can give different just a natural language requirement in terms of like how to describe some safety critical scenarios, and we can give different requirement and like reminders or constraints to constrain the generated scenario to follow certain like constraints, and also ensure the safety critical like challenges here. And then after we have like these simple interactions through, say, the chat interface with, say, ChatGPT or other large language models, we can actually connect it, and by building a retrieval database in terms of connecting the language descriptive scenarios towards certain action functionalities itself, such that those action functionalities will directly connect to the domain-specific languages, so that these domain-specific languages will directly generate those scenarios and then map to the actual simulation environment. Either here we use Scala as an example, but we can connect to different simulation environment such that we can have an end-to-end throughput through the NLP description towards the corresponding scenario generation testing in the simulation environment. So with this, there are some very quick examples of such safety critical scenarios we generated. For example, here on the right-hand side, you can see this is by some prompt engineering and then diverse scenario generation and guidance. So you can see exactly it will follow the description of the ego vehicle while driving towards a straight road and then have a pedestrian coming out suddenly from a hidden object, which is very dangerous. And similarly, we can construct such scenarios like vehicles changing lanes, and then it will be quite important scenario for real-world testing for the safety testing itself. And similarly here, there is a left turn. Basically, I want to show that we can construct different diverse scenarios that we can think of, and we can prompt the model to help brainstorm in terms of the diversity of the scenarios. And now it becomes very straightforward and easy and efficient to generate and test such scenarios with such, I would say, scenario generation pipelines or attack red teaming pipelines to do the stress test for the autonomous driving vehicles. So with all this, the thing is that, okay, we can generate a lot of safety critical scenarios for testing. That's also part of my main focus in the previous research and the report. And the next, I think we are entering the stage of now we have been able to generate a lot of efficient and effective safety critical scenarios for testing and analysis. Then how could we provide some safe driving or safe algorithms which can take care of multiple factors? For example, there are several questions we want to answer in terms of, can we leverage, say, foundation models to take multi-modal like video, text, images and audio, those multi-modal information as input to jointly optimize the decision-making process and make it more automatic and advanced. And second of all is that we know every such learning-based approaches, they are all data-driven currently. Therefore, if we have some real-world safety scenario, safety rules, for example, traffic rules and driving rules, which we human know we should obey, and can we enforce the model, the data-driven model, to follow those rules? This is a big unknown, and it's very important. We all know, but we have no way to explicitly integrate those knowledge currently, right? So we can only say generate more data following those knowledge guided distributions such that we can train the model again and again, and hopefully it follow. But there is no way we can explicitly do that, which is definitely critical. So here, I think I want to dig into a little bit more on that because that's very critical and the novel point I want to emphasize so that we can look at how we can actually integrate the real world knowledge explicitly to some data-driven models that we use now, including foundation models. Like here, I give an example of vision language models like multi-model foundation models. So here is an example that there are different real-world scenarios for, with snows and the relatively diverse, traffic scenarios. And with this, on the very high level, we can see that assume given a, say, multi-modal foundation model, we can take those video clip, these are video clips, but we can directly take the video as input and the model will be able to extract some existing statistics such as speed, some curvature and acceleration, basically different detailed low-level information of driving. And then based on the model output, we can accomplish several tasks. One is some high-level action prediction. For example, human can ask the model, say what should be the next action itself, and also give a reason with the model, like why you think the next action should be this rather than that, and etc. So this will make it more automatic and debuggable, so we can reason with the model itself. And another level of functionality is we will exactly provide the low-level action prediction precisely, such that we can provide trajectory prediction and driving prediction directly. So with these two high-level function, two functionalities, high level and low level, the goal of us here is to ensure that how we can provide a unified LM, or foundation model, multi-model foundation model, as safe as possible for real-world deployment for such safety-critical scenarios such as driving and aircraft. So first of all, let's see. So basically, on the very high level, intuitively, for example, for these types of high-level action prediction, intuitively, we can say leverage some similar experience. For example, some videos in similar scenarios and similar, say, types of vehicles, etc., so that we can leverage some past knowledge experience to help, right? And we can discuss how we exactly leverage that. And the second is that we hope to provide some safety verification based on safety rules that we have, such that we can do some hopefully post verification, which means it will not hurt or delay the efficiency of the model prediction itself, but it will provide verification to ensure the safety and stop the unsafe actions on time or almost in real time. Depends on how large knowledge set we have. And on the low-level action prediction, basically the metric or the success criteria is that how we can make it as accurate as possible and less hallucinated, and we can provide new loss functions to ensure such preciseness, which we will show later on. So basically, on the very high level, I will talk about quickly three concepts in terms of how we leverage past experience, how we leverage existing knowledge and explicitly integrate them and provide safety verification, and how we design loss functions to make the low-level action prediction to be as accurate as possible. So three-level things. So first of all, as we mentioned, I think one of the most important things that I want to emphasize here is how we can explicitly integrate, say, some driving scenario, driving rules and knowledge into, say, autonomous vehicles and air flights, such that we can enhance or even verify their safety, which is very important, right? And this is a high-level example. So I want to show that a mechanism that we can leverage to explicitly integrate safety knowledge. And this is one way, and hopefully we can use this as an inspiration to have different mechanism and approaches as well. But I want to emphasize that currently there is no way that we can explicitly integrate the safety knowledge yet if we rely on the data-driven models, unfortunately. So therefore, I think that's a very important thing or component that we need to think about. So, okay, on the very high level, this is an example, say human tell, say a model or a pipeline in terms of the historical action sequence in terms of speed, like acceleration and other things. And we'll give a video. This is the concrete input, and we'll give a video as input as well as a multi-model input. And then we'll ask what's the model, what's the next high-level action prediction. And the idea is that, first of all, with this historical information, we can extract some similar experience, for example, using certain RAG to extract the information. So we'll discuss this a little bit later. Basically what's unique thing we can do to make the RAG here more precise. And the second is, which is the most interesting part I'm most excited about, is we mentioned how we explicitly integrate the knowledge. So basically here we have different knowledge. Say we can map the knowledge into first order logics. Say if a stop sign, you should infer decelerate and stop. And say if there is a yellow line, solid yellow line, it's infer that you should not bypass it or cross it, things like that, right? We'll show some examples of the knowledge rules we have later on. And with this, we can integrate or embed the first order knowledge rules into a probabilistic graphical models and put the model after the data-driven models such that the goal is whatever predictions the model give, and then it will pass through the post safety checking graph itself and give result in terms of say some of the rules have been violated based on the action prediction here, or if not, if no rules are violated, you will just keeps original answer. If rules are violated, then the action prediction probability will change such that until the probability distribution satisfy the knowledge rules, which means after the probability of different action changes, your action can be updated. For example, here in this case, first of all, the model answer we should move forward, and for some knowledge rules, it is violated, and we can see the example later on, and then we can see the model actually go back to redistribute the probability for different action predictions, and eventually the model output the correct action prediction as stop. So because from this historical information here, you can see the front car actually start to decelerate, and therefore the car should decelerate or stop. So that's the high-level rationale here. So the idea is that we leverage the probabilistic graphical model to embed different knowledges, which is represented as first-order knowledges, such that the model will never violate the main safety knowledge that we want them to obey. So in this way, we'll be able to achieve what we mentioned, explicitly enforce the rules or not some safety related knowledge to be satisfied. Second of all, it's efficient because we don't need all the rules here. It's a post checking and it's not stuck during the inference time, so that the inference is as efficient as whatever models previously we have, but just with the post checking, it will automatically update the prediction if the previous prediction is incorrect to ensure all the predictions satisfy the safety rules that we want to enforce. And third of all, the benign performance accuracy will not be hurt because we know there sometimes will be a trade-off between, say, benign performance and safety or robustness, right? But here, because this is a post-safety verification or checking, such that if no rules are violated, for example, so all the results keep the same, which means the accuracy will be the same with whatever the model before. But if any of the safety rules is violated, and then the safety checking component will be triggered and it will be updated so that it will be at least as good as the original model, but it will be much safer based on what safety knowledge rules we give it. So this is the part. And third of all, as we mentioned, so basically here, because of the rules are violated and it will be rejected and it will update the model with the correct action. And finally, we can provide different loss functions to, based on the correct high-level action prediction, we can provide more precise low-level action concrete like a speed or acceleration number here, because as if the high level action prediction is wrong, then the low level one will always be deviated. So this is a high level structure of how we can leverage, say, similar experience like post safety verification and advanced loss functions based on the correct high-level action to provide precise, accurate, low-level action prediction. So just very quickly, let me give a little bit examples of the the safety enhancement for post-safety verification. And I will skip the other two parts due to the time limit, but we can discuss more if you are interested. Yeah. Okay, so here basically the process of the safety rule integration and the knowledge enhanced safety verification looks like here. So basically want to ensure the action of the foundation models to follow the exact traffic rules. And here we want to explicitly integrate it as we mentioned. So then the process is that basically you have a video frame, and we can use different models to extract the scenarios here. For example, whether there is a red light, whether there is a yellow, like a solid line, and whether there's a car in front. So basically, all those predictions are formed as a predicate here for model like a solid line, yes or no, such as light. And then we have formula like a knowledge rules to connect all those predicates. For example, if it's solid red light is true, then it indicates you should do decelerate or stop, and you should definitely not accelerate, right? So there are some like knowledge rules here, and then we can train the model with the weights, and then using by embedding those knowledge rules directly. So I will omit some details here, and then basically with this we can see we actually leverage the California driving driver book to extract around 60 safety knowledge rules and embed it to the first order logics, and then embed to the probabilistic graphical models as we mentioned, and then we automatically extract. These are some just a quick example of action predictions and the conditional predictions, and these are the rules that we extracted. You can see it's actually very basic rules, but surprisingly, as we know, the model, even with such basic rules, the model will violate sometimes, which is like not what we want. So we want to ensure that the model at least enforce and follow those rules exactly. And with all this, I want to give an example quickly, is that, for example, here the human will ask like what's the action, high-level action should be, and the model will say something like, we have the identify the red light and the pedestrians, and based on it, will predict the action like this, and then the human will actually ask whether it should going forward, and then the high-level action will be verified here based on the knowledge that we have. And very interesting, we have some statistics looking at different actions, like which types of action is easier to violate or not, and there is some distributions here, and it's interesting to know usually what types of actions is easier to be violated against the traffic rules, and apparently that is also related to their own action frequency as well. And we can see by adding such action predictions on the open BDD benchmark dataset, it can got almost a 10% improvement in terms of the accuracy of high-level action prediction. And lastly, there's one very quick example I think is very interesting, that the ground truth is a car should stop. And then based on this, we can see actually the original prediction is the car should move past on the right, because clearly there are some like empty spaces so that it can go to the right and move. And then the violation rule is that there is some solid yellow lines here. It's actually not that obvious, but the model is able to pick it up, so that it says that if there is solid yellow line, you should not go left or right path, and then the car actually change the original action to be stop action based on the rule violation. And yeah, there's another example for red light, which we also look at it before. So overall, on the very high level, actually with such integration of knowledge rules and other like past experience integration and the loss function improvement, we can achieve like more than almost like a 10% improvement, and improvement of like 69% high level action prediction, because it's very powerful, especially for high level action predictions, and the models are not that good currently yet, and it's also like achieves the top one place in the open autonomous driving leaderboard for safe driving. Yeah, with that, there are some useful links. Thanks, Edward. We hope we can have time for some questions. Yeah, thank you.
Thank you both for this wonderful talk. I'm afraid this time we don't have the time for Q&A, so we'll defer it to the later discussion session. In the meantime, do we have Chuchu here? And
yeah, can you hear me?
Yep, I can hear you.
Okay, let me share my screen.
There is a question for Bo in the chat. Maybe she could answer in chat from Michael.
Yeah,
Yep.
yeah. Okay, I can quickly answer that while Chuchu is setting up. So I see it like whether we consider the safety, hierarchical safety environment, for example, some safety situation you might require to violate safety rule if no other choice. Oh, that's a very good question. So those special scenarios could be integrated as rule as well. Say if this happens, for example, it's an ambulance car or things that you can like have some exceptions for the rules. So those are exactly can be integrated into the probabilistic graphical models to enforce as well. Currently, we haven't yet, but I think, yeah, that will be a good next step. Yeah, thank you.
Okay, so I think that's the answer from Bo, and Chuchu, you can go ahead.
So you're able to see my screen?
Yes.
Okay, great. Hi, everyone. This is Chuchu, and I'm happy to present our ULI project year 2 update. And this work I'm talking about today is have some similarity to Bo's work for the testing and test case generation, where it's taking a slightly different approach, a Bayesian-based approach. And the work is done with my student Charles and Anjali. Charles recently graduated and joined the Department of Energy to use some of these methods on the power grids. So our task is under TC2 fast and the data-driven and code-level verification. So basically, once we take this learning-based system, we want to answer a few questions. How do we predict when things could go wrong? And how do we fix these failures, especially fix the failures without making another one appear, and to overall improve the robustness of the design to make it verifiably safe. And lastly, we want to debug the system if any failure or any unexpected behavior appears. So complex systems, especially in this project, we are looking at systems that have a lot of learning-enabled components. They are very difficult to debug, and even for experts, it's kind of like quite difficult to isolate the bug. For example, a bug could appear at the visual observation module. And because once the system has been integrated, it's not easy to isolate this bug because anything wrong that happened at the observation or sensor level will be further propagated to the machine learning model that is taking the sensor information to either process information or do the control and planning. And this error will continue to propagate through the entire computational pipeline, through the planner, the controller, and we know that once the control make the wrong decision to move the vehicle, the visual observation will be further dragged to the wrong direction, and this error will kind of accumulate and probably will see worse and worse behavior without knowing which part actually went wrong. So this complex system to debug is very hard to debug or to isolate where things can go wrong. We want in this project to take more of an end-to-end approach to have this pipeline of design, test, and debug. Especially in this talk, I want to mention our recent effort on design and testing, where testing is to predict likely failures, and we will also use these failures to mitigate the potential failure in the design to further improve the design, ultimately with the goal of have a verifiably robust design. And of course, there will be another component of debug to infer the root cause of the failures. We will leave this. I don't think we will have time to talk about today, but we'll continue to work on this and leave this for next year's update. And all the things I'm going to talk about today are described in these two following the bottom two publications, and has been used on a very wide range of applications with the focus on the aero applications. So our contribution here to use testing informed design have the following highlights. We improve the robustness of the design from simultaneous failure prediction and repair. And we want to improve the design by finding a diverse. Bo mentioned the importance of a diverse set of failures, and we also want to generate highly risky failure modes. And we also want to show better scalability and flexibility in terms of handling both known models, white box models, and black box models, and with special purpose tools. So the mathematical framework we are using for this testing strategy is the following. We're going to take an end-to-end approach where we're going to look at the entire system, like including all the modules as a simulator. And this is basically basically our entire system, but a lot of those parts, like the planner, the perception, the control, will be code. And this means we will have some sort of access to the execution of the system. And we will view the system as some sort of like a machine that take two type of input, X and Y. Both are vectors. X define the design parameters. Those are the parameters that we could play with. We could tune. It could be the neural network weights and biases in the machine learning models. It could be the coefficients of certain controllers, or it could be anything that we as engineers could change in the system. And Y means the exogenous parameters or the external parameters that we cannot really change. So on top of this system or the simulator will take into the two set of parameters and generate some sort of behaviors. And on top of this system, we will define like what is ideal or a type of behavior using a cost function called J. And this J can describe a lot of things like the goals, the safety constraints, the limits, like the actuation limits, and any other thing that we think is important for the system. Now with that, design basically now means that we want to find the optimal set of design parameters that will optimize this cost J. And similarly, the testing problem basically want to find the set of parameters Y that will violate some sort of a safety constraint, which translate to maximize the cost function J. So in this way, then this testing and design framework will become a two-player game where the designer basically will find the optimal design parameter, and the testing, as a testing engineer, we want to find a set of failures that will violate the constraints and give us a high cost. And this cost can also be associated with the risk that we care about. Now, at a traditional approach to solve this two-player game is through adversarial optimization. This can improve the robustness, but there is a risk of overfitting. And that is exactly the problem we mentioned earlier. How can we fix this problem without making another one appear? Basically, if we have some set of failure modes and we want to improve the design against these failure modes, and we will probably find a possible solution like the trajectory here to avoid a local obstacle. But if we turn to the other player that is playing with the exogenous parameters, we probably can easily find another failure case because the previous design actually overfit to the previous failure case. And we may keep doing this, so on and so forth, but at some point, we might be pushed to a corner that we just cannot solve this optimization problem anymore. Now, a simple thought is, can we just remember all the previous counterexamples? So here, basically, without just optimizing our design parameter against the previous round of failures, we just remember all the previous failures and try to optimize against all of them. And this could potentially give us another solution that avoids the issue of overfitting or trapped at a local optimum. So that is the idea. Basically, we want to ensure safety, and we know that successfully handling one or a small set of test cases or counterexamples does not mean safety. We want to generate a diverse set of testing cases. And at the same time, we also know that for very well designed systems, failures are very rare. So if we just use random sampling to get to those failure modes, these are not good enough. We want to be strategic about finding those failure modes. We also want to find the high risk counterexamples. We don't want to spend the majority of our testing resources to find those mild cases, but we want to hit those corner cases. Now, why it is very hard to find diverse counterexamples? Bo has mentioned a couple of thoughts there. From an optimization perspective, finding diverse counterexample in this framework basically means we want to find different type of local minimum, local optima that correspond to the failure cases that can cause a high cost. If we use like the traditional gradient-based approach, we all know that every local optima will have a local regional attraction, and it really depends on where we initiate this procedure. And depending on where we initiate this, all the algorithm, gradient-based algorithms will likely going to convert to the nearest local optimum. Of course, there are a lot of versions of the gradient-based approach that we introduce different technologies here to get rid of this local optimal problem, but there's not a uniform good way to ensure that we will always have a larger regional attraction. For this particular problem, we actually think that we can reframe this testing problem from an optimization problem to a sampling problem, because sampling turns out can recover the diversity much better than the optimization for test case generation. So instead of doing gradient-based optimization, we're going to use a cost function to inform us a density distribution, and we are going to sample according to such a distribution. And for example, if we use a very well developed algorithm called the Metropolis Adjustment Langevin algorithm, then we can see that the region of attraction for each of these local optimal basically is the entire state space. So we think that sampling can recover the diversity, and also we can introduce the idea of risk here by increasing the cost of the risky cases. Then the sampling problem, the sampling algorithm can also pay more attention to the areas that is their higher probability, which translates to higher risky cases. So then the mathematical framework basically takes two steps. First, we will balance the failure likely modes with the severity or the risk of these failures. Then instead of optimizing this cost function, we will sample from the posterior that is mimicking the cost function, to use this cost function to construct the density distribution for the sampling. So this approach, basically, we want to generate high cost and high risk failures. Now, basically, we want to start from the prior distribution of basically the distribution that only describe the risk to the distribution that will give us diverse and high risky cases. To do this, we can employ a very broad range of different sampling approaches that are MCMC-based sampling, including both gradient-based approach and gradient-free approach, like the random walk Metropolis Hastings approach that can get rid of the issue that some of the code that we have do not directly give us gradient or do not give us good gradient. And also we introduced a annealing type of approach. Instead of directly sampling from the posterior, we will add a coefficient lambda here and gradually increase the value of lambda from 0 to 1. And we can see that when we gradually increase this lambda, this is very similar to the annealed sampling or the annealing algorithm in many as a meta heuristic. This can allow us to explore a lot of different multimodal failure spaces. So this is this is the part for predicting the failures. We're basically going to perform the failure prediction through sampling according to a severity adjusted posterior cost function. Now, similarly, if we want to design the update, it's actually almost a similar process. So instead of maximizing cost, the design wants to minimize the cost against the previously discovered failures. So we just need to basically employ the similar procedure, but inverse the sign here at the cost function. So have a minus lambda j. And of course, we can gradually increase this lambda to mimic this annealing procedure to find a diverse set of failure modes. So this design update basically will mitigate the failures that we find in the previous round, and we can convert back to a failure prediction, then fix the previous set of failures through another round of design updates, so on and so forth until the algorithm converges. So I want to present a few case studies that we have used for this line of the testing framework. The first one is closely connected to what Evangelist has been doing. So Evangelist has been at Georgia Tech. They have been working on the MPPI controller for a very long time. And at Georgia Tech, there is a testing there's a test bed called the Auto Rally test bed. Basically, there's a racing car trying to travel through this track. Now, the testing problem, we have a few testing problems here for the MPPI controller. The MPPI controller is particularly difficult for the traditional testing approach to be employed. First of all, there's no direct gradient information that we can just grab to have a gradient-based approach for the testing. And also it's a receding horizon controller. That means we don't have a good closed loop description of the entire closed loop system. That means the traditional verification and testing method cannot be used here. And for this racing car on the track using an MPPI controller, we are asking a few questions as a testing question. The first one is the one I'm going to present here, is the obstacle placement. Basically, the question is, if there is an obstacle that appeared on the track, and of course the obstacle is smaller than the track, it's not going to completely block the track, where should we place the obstacle that can most likely going to cause a failure? And the second question we want to ask, which I won't have time to present today, is how, if we are going to change the track, what type of the track will be most difficult for the MPPI controller to travel through? So I'm going to show you the result of the obstacle placement result here. So to use our framework to find the place to place the obstacle, we still need two more steps to make it work. Sorry, I accidentally clicked the mouse before we can directly use. The first is the obstacle we only want it to be placed on the track, not everywhere, like outside the track. So here we employ a kind of like an engineering trick called a neural projection operator. So basically, when we sample, we can still, it's very difficult to sample on the track. We will just sample from the entire state space, but we will have a neural network, a very small neural network that is trained to learn the decision boundary of the racetrack and like think that an area that another racetrack. And this learned classifier will help us to project all the samples onto the track. Now, all the samples, all the test cases we generate will only be the obstacles on the track, not outside it. And the second, a second method we used here is to, on top of the traditional first order line-driven algorithm, we actually add momentum here to have the second order line-driven algorithm, because this can lead to faster convergence and a more diverse failure discoveries. So the idea here is if we are going to only have a very limited number of samples, we want to discover the high risky areas. So here, for example, the rightmost one is just the random walk. And we can see that we will need to use a large number of samples to identify the probability of a collision if the obstacle appears here. And this the bar here, the more like the yellow or the light the color is, that means the probability of collision will be higher. But we want to only use a very limited number of samples. Using second order line-driven algorithm, we can discover the most risky areas for placing the obstacle. And here is the demonstration while I talk through. For example, among all the places, our algorithm can tell you that if the obstacle is placed here, this has the highest probability of a collision of the car. And actually, sometimes it's not the collision of the car to the obstacle. It is it's a collision of the car to the boundary of the rack, because the car is trying to avoid the obstacle. I hope the video is smooth here. In this case, you can see this exact position of the obstacle. It's a virtual obstacle we put here. We didn't want to damage the car. You can see that the car directly bumped to the obstacle. And we can theoretically show the probability here is also 94%. And a second type of failure is another interesting failure where a single obstacle placement may not cause a very high probability of collision. But if we put two obstacles in a certain way together, then the probability of collision is significantly higher. So the first one is 61%, the second is less than 40. But if we have these two, then the probability of collision is not 61, it's actually 81. So here we also have this demo of showing you. You can see that the very shortly we will see the car was trying to avoid the first obstacle, and it was quite successful of doing that. But because of the collision avoidance with the first obstacle, it didn't have enough actuator effort to be able to avoid the second one, so it crashed to the boundary of the track. And here, another thing I want to mention is we did not collect any data from the hardware platform. Everything is simulated and analyzed in simulation, and we directly deploy this virtual obstacle here and run the original MPPI controller. That is actually having a very high success rate, if I think approaching 100% no collision rate when there's no obstacles. Okay, and this same framework can work across many different applications and with very high dimensions of both the design parameters and the exogenous parameters. So we can see that among all the examples we have on the robots, the team of robots, power grids, fixed wing, ground collision avoidance problem, manipulator problems, satellite problems, we can handle thousands of dimensions for the design parameter as well as thousands of dimensions for the exogenous parameters to find those failures. And this picture here want to show that if we use this iterative process to find the failure and use the same process but inverse the cost function to minimize the cost function for the design, we can end up having a much more robust design of the system. We have this a bunch of different vision in the loop control tasks that is under testing. We can see that our approach will end up giving you a much more robust design that will have lower failure rate and a lower cost across different examples. And I want to show here two environments that are more related to the more closely related to the flying robots. Here, it's a quadrotor trying to fly across, like we're actually trying to simulate a forest. And this quadrotor has like a camera to see what's happening, to detect the obstacles. It has a full perception loop, and you can see how the repaired policy can avoid the collision while staying on course to land exactly on the pre-designed landing zone. And even if we move this, change the obstacle from static obstacle to moving obstacles, the initial policy would crash. It's a reinforcement learning policy, but the repair policy can recover from those early disturbances caused by the moving obstacles. So last slide. So for next year, we are going to continue this line of work. We're going to focus on the last piece of the root cause analysis for the existing failures that has already occurred. We want to be able to isolate and figure out where this failure happened and what is the most important factor in the entire system that could cause this failure. We will integrate this algorithm I mentioned into the VERSE tool. That is basically the tool we want to jointly develop with Professor Mitra under TC2. And we're going to work with Professor Mitra and other TCs to provide assurance cases for all the demos. And once we have those demos, we also want to understand what has caused if there's any failure case, and we want to generate more test cases from the very limited hardware demo that is going that we are going to observe in the May demo day. So that's my presentation today. I don't know if we will have time, but happy to stay on and answer questions.
Thank you, Chuchu, for the talk. We actually have a gap time for 5 minutes before our next speaker. So we can host questions for 5 minutes. If there's any question from the audience, now is the time.
So Chuchu, thank you. That was a very nice talk. The question I have is if you take what you've done with Georgia Tech Rally Car and reproduce it with urban air mobility vehicle, because there's some concepts of using corridors for containing the vehicles, and then things happen, right? Whether it's vehicles, multiple vehicles, etc. What would it take for you to reproduce that environment and to run that study?
Yeah, thanks for the question. That's a very, very interesting question. That's definitely something we're looking at. So one important thing we are looking at right now is basically like to learn from the limited failure data to figure out a few things. The first is what has caused this failure, to do the root cause analysis. Then we want to be able to generate a similar set of failure cases that's not just reproducing, but because we know the failure, we want to learn like this is the most sensitive part, and by triggering like more disturbances in this area, that will likely going to generate very similar failures in a similar situation. And that is the problem we are looking at right now. So that's basically we want to be able to like collect the existing failure data and have this system and have this either the simulator or some understanding of the system to be able to reproduce, not only reproduce what we can see, but also can generate a set of diverse failure cases that can cover what we have seen before. That will be my short answer. And of course, to be able to do this, we will need a relevant simulator or simulation environment that all the different teams care about.
Okay, thank you. That's a good short answer. Maybe we can chat offline of how we can integrate the JAX Guam with maybe Carla or some others to create that environment for you so you guys can actually conduct that experiment.
Yeah, that would be wonderful.
Thank you.
Thanks.
Hello, Tutu. Yeah, I have a question for you. Actually, I have two questions for you, so I'm not sure how much time you have. The first question is that, to my understanding, you are using an accept-reject method for your samples. And typically, an accept-reject method comes with a probability of accepting. Is there a chance that the design problem, essentially, that you're having is going to result in a very high probability of rejection? In that case, what do you do?
Yeah, that's a very good question. So in the design process, if we, sorry, I didn't like mention all these detailed, very, very detailed technique here in the presentation. So in the design process, if we like use like exactly just the accept design reject sampling algorithm, there is a large chance that we're going to reject the good design. And we also know that the design itself is not exactly a sampling approach. It's more like the good design may lie in one of these, good samples, but we may miss this good sample. So if we use exact that method, so the approach we have been taking is to use this the Metropolitan Langevin algorithm at the initial round, but when we are getting close to a good answer, we will actually convert back to a gradient-based approach to be able to have a more deterministic answer to find the good design. So it's more of like iterative method. We will like switch between the two. One, the first to use the sampling, and then at some point convert back to. It's kind of like the, for example, the simulated annealing. At some point, if you change the temperature to very low, then it will become a local gradient-based approach.
Thank you, Tutu.
Mm-hmm.
So,
Thank you. Sorry, Yanis. Well, I think we're running out of time, and we can keep the discussion in the later discussion session in just 10 minutes. And now, our next speaker is Aaron Ames from Caltech. So do we have Aaron here?
Yeah, I'm here. Hi.
Okay, wonderful. Yeah, can you share your screen and take it from there?
Absolutely. So first, let me say thank you all for inviting me to this event. The little I've seen is really exciting. All right, let's make sure I'm doing this right. Everyone can see my presentation, yeah?
Yes, we can
Good.
see it.
Okay, great. Thank you for inviting me. So this was sort of auspicious that we flew on the Vista aircraft recently, and I was asked to give a quick summary of that flight from the Caltech side. And this was done in collaboration with 3 Laws Robotics, which is a company that spun out of my lab using CBFs. So let me give kind of an overview. I'm assuming that a lot of people on the call are familiar with barrier functions and control barrier functions, but to kind of give context for what we deployed, a quick, let's say, refresher on CBFs. The idea is you start with some controller that might not work properly. We just saw, for example, learning-based control. This is one example where there might be edge cases or there might be collisions with the environment. In this case, this was a nominal controller on this big rig truck, the one in blue. And that truck didn't know the van was actually in another lane. So it braked late, and this would have resulted in a collision between the van and the big rig truck. And so what barriers do is give a safety layer between the nominal controller and the actual system itself. In particular, you instantiate the safety filter, which is, nominally it's a quadratic program, which takes your desired input and filters it based on a CBF condition as given by inequality represented by a constraint in a QP. And so doing this in this truck example, you get this safe braking behavior, right? So the nominal controller was driving the system to an unsafe condition, and the CBF with an additional barrier on this sort of time distance, this time headway distance, results in safe braking. So this is the basic paradigm of safety critical control with CBFs. One more example and kind of a quick snapshot of the math, and then I'll get to the aircraft examples. So again, on the left, you have a nominal controller. In this case, it's one that's driving a Segway. This is a student that's driving a desired position on the Segway, and you can see the desired reference signal going up and down and ultimately crashing the Segway itself. And then on the right, you see what happens when you filter this with a CBF condition. These conditions, the CBF condition is based on a theorem that is a decade old now. So it first appeared in 2014. That basically said if you satisfy this differential inequality on your barrier function, the Lyapunov-like condition, it's necessary and sufficient for forward set invariance, which we call safety. So you imagine you want to stay in your safe set, avoid obstacles. This guarantees a ways to do that in a differential inequality. The important part of this specific example that I'm showing here is that this can be done on not just collision avoidance constraints, but stability constraints. So in this case, we're actually constraining the Segway to stay upright while we're trying to avoid collisions with the environment. And that's really important because these more complex dynamic constraints are what we use in the context of aircraft. So you can't just do collision avoidance with a simple model to avoid hitting an obstacle in the environment when you're flying a jet airplane. You have to actually acknowledge the physics of the system. So with that, let me give 2 more quick examples in flight, and then I'll get to aircraft. So this is collision avoidance now on a drone. So it has onboard sensing, onboard computation, and it's told to go to a position beyond the obstacle. It stops, and then when my student moves the obstacle, it continues on. More relevant to the aircraft example is this one. So this is a paper, you can see the reference down there, is doing geofencing. And the method and the way we do geofencing on the drone here is actually very similar to what we implemented on the jet aircraft. So if you're interested in more deep dive into the math that we did, this gives you a preview if you look at this paper. So in this case, we have a high-speed racing drone, again, all onboard computation, onboard sensing. We're using a GPS signal to determine regions in the environment that we're not allowed to leave. And then we have a drone pilot that's trying to fly this drone outside of these regions very aggressively. So we're doing what would be termed assaulting the limits in the context of the geofencing, and we're doing it at speed. So in this case, the drone's flying at 100 kilometers per hour, so very fast. And you can see the geofence there. And so to stop before the geofence at these kind of speeds, again, you really have to account for the nonlinear physics of the system, which the barrier function does really well to enforce this braking. So that's kind of the background. Again, there's a ton of papers on this. I don't think I need to go into a lot more detail, but I wanted to kind of set the stage for what we do on the aircraft itself. So on the aircraft, we really want to do this exact thing. So we want to instantiate a safety filter on the aircraft. What this is termed in the context of the VISTA program is guardrails. So that's what we call our safety filter on the VISTA aircraft, is sort of these virtual guardrails. Think about them as force fields. We first investigated this theoretically in the paper that's linked here if you want some details on doing CBS for fixed wing aircraft. And the idea is fairly straightforward. You have your model, which in this case can be a fairly reduced order model. You can do a variety of different sort of nonlinear dynamic models of aircraft, sort of kinematic models, kinodynamic models. The model can vary depending on what you want to achieve and what your inputs are to the system. But you do have to consider some nonlinearities. And then with that, you can synthesize barrier functions. So what I'm showing here are the two barrier functions for geofencing and collision avoidance. The point is you can write down these constraints pretty simply. Of course, then you have to come up with the control barrier function kind of conditions that result from these. And the end result is these sort of conditions. I'm just showing them on the top for those that are mathematically minded. This is what the conditions actually look like based on that nonlinear model. But more maybe relevant is the specific application. So we can do collision avoidance. So in this case, the two aircraft were on a collision course. The barrier function steers the aircraft that you're controlling to avoid a collision with the other aircraft. We can also do geofencing. Again, in this case, the nominal signal to the aircraft would have been flying straight. There's a geofence, which was in this case this plane, and it steers away dynamically and avoids the bad region. And then you can combine these together and do collision avoidance and geofencing. A big part of the implementation on the aircraft is we need to do multiple CBFs simultaneously and in a way that respects the physics of the system. So you'll see more of that later on the VISTA aircraft. So let me jump into it on the VISTA aircraft itself. So this is all hot off the press, and I have to say none of this is public yet. So you're the first people seeing these results. So the objective was to do CBFs on the VISTA aircraft. So let me give a little background. So Richard, Murray, and myself have a project with AFOSR and Brett at AFOSR. And over the years, we've developed methods to do safe test and evaluation of a variety of systems, including aircraft. So we had developed this fundamental science, and then we had the ability to translate it to the VISTA aircraft through an effort from the AFOSR as well. To translate it to the aircraft itself, as I mentioned, we needed some professional engineering to do this right, because it's a very complicated problem. And I have a startup that worked in this case to really provide this expertise on CBF. So that's 3 Laws Robotics. So it was a collaboration between AFOSR, Caltech, and 3 Laws Robotics. And in particular, what we want to do is implement limits, a variety of state limits, G limits, geofencing, alpha bounds, etc. We didn't implement all of these limits yet experimentally, just for lack of the ability to do tests. We didn't do as many tests as we'd like, although we did a lot of tests. We ran about 22 experiments on the aircraft. And we implemented this, again, just recently in September of this year. So first, just to kind of give you a snapshot, the system model is on the right. It's a very standard model, comes from Sean Stevens' PhD thesis at AFIT. And then the way we implement the safety filter on the aircraft system is indicated on the left. So we grab these roll rate, pitch rate, NZ. So this is this sort of normal acceleration that the pilot would feel, and then we modulate those signals depending on the safety constraints in the system, and pass that to the controllers that are then being run. Specifically, Lockheed Martin type controllers are run under the surface, and we pass to them. So a lot of the interfacing was with the Lockheed Martin and their simulators. So the 3 laws visited Lockheed Martin, ran this in their high fidelity simulator. We also flew our software, only our software. We didn't do any control actions in May for the first time. So actually, it turns out that the Secretary of Air Force was on the plane testing out the new DARPA ACE pilot, or that was the reason he is visiting Edwards. And our software was at least on the plane monitoring what was happening, getting data, but we didn't actively fly yet. So based on the May flight and the data we received in the APIs, and based on the integration with Lockheed Martin, which happened over the summer, we ultimately flew on the aircraft again between September 9th and 14th. We had 14 test points that were flown over 5 flights. What's really interesting about this is that they were testing out the L1 adaptive controller at the same time. So we got to ride along to those tests and actually sort of run in tandem with the L1 adaptive controller, meaning when they were going to test points with what's called the Have Spice program, they would turn on our CBFs, run a couple test points for us, do some test points with Have Spice. So it was really cool that both the L1 adaptive and the barrier functions were running on the same plane, although we didn't analyze their intersection yet. It would be very interesting. We had 100% success point in hitting all our test points, meaning we had no failure of the algorithm, no failure of the safety constraints, even under the pilots assaulting the safety limits all the time, really aggressively. And again, what we tested in particular were G limits, geofences, altitude, floor, and ceiling, and all combinations of the above. So those were the safety constraints we considered. The other interesting and important thing is that all of these safety constraints could be modified online on the fly. So in particular, we didn't even get our specific geofences until the plane was on the runway taking off. And we inputted that data into the CBFs, which were, as parameters in the CBFs, and then implemented the geofences on the fly. So let's look at the first experimental data. This is the test card before I do that, for those that are familiar. These were the different test scenarios we wanted to test, and we ran through all of these test scenarios, these test points. So this is what the data looks like. Again, let me stress, this is the first time this data is being seen by external eyes, let's say. Please don't share this data yet. So it's a little noisy and messy, and these plots are not paper quality yet, let's say. But it really does show well what's happening in its rawest form. So I didn't include, we have a lot of experimental data because we ran a lot of flights. Like I said, I think we have about 21, 22 total experiments over 5 flights. I just picked out a couple of the relevant ones to give you a sense of things. So first, on the left, we have assaulting a altitude ceiling. So in this case, it's engaged. Once it's engaged, the pilot actively assaults the ceiling and isn't able to violate the altitude ceiling. The same thing with ceiling and floor. So now we're doing a combined between ceiling and floor. And it's important to note we're doing G limiting through all of these, meaning we don't allow acceleration to go outside of 4 Gs, which is very important. So you see the pilot commands are really, really aggressive. So they'd be commanding like 20 Gs. And we don't let them do that because that would be very bad. We can combine this with geofencing. So in this case, you can see all these different points where you don't violate the altitude floor, and the pilot keeps approaching the geofence. That's the red line on the top right, keeps approaching the geofence and it doesn't violate it. So a couple more examples just to kind of zoom in on this. So again, on the far left, the geofence isn't violated, the ceilings aren't violated, and you can see kind of the difference in response. So in the middle plot, where in one case the plane just flies there, the pilot just kind of lets the CBF take over as it's close, and then it turns away. In the other case, the pilot actively assaulted the geofence, meaning took the stick and kept slamming it into the virtual barrier given by the barrier function, and in both cases, we maintained safety in all the limits. So I'm sort of at time, so let me just show the videos without further ado. So this is the G-force limiting now. So you can see the live plot on the top right with the data we collected. So in this case, the pilot's doing a hard stick pull trying to really crank up the G-force, and we're capping out the G-force with a barrier function on the G-force. And then when the pilot comes back, he gets full control authority. And so this is really the key part here is we only take over. CBFs only do an intervention when the pilot command would do something that's unsafe on the system. This is geofencing now. So you see the geofence, that's a physical region in space that we can't leave. The pilot is flying directly towards the geofence. So at this point, CBFs take over the guardrails and is actually turning the plane. So we're turning the plane, meaning the CBFs are turning the plane so that it flies parallel to the geofence while not violating the geofence. And then once the plane's in a safe configuration, meaning it's flying in a direction where safety won't be violated, it hands control authority back to the pilot and he gets back with 100% control authority, right? So and by the way, I should say at the same time we were approaching the altitude floor. So there were actually two barrier functions simultaneously active, the geofence and the altitude floor. So that's the summary. Thanks for inviting me. I won't go through it because I went a little long. I apologize for that. But I'm sort of excited to report the first example of the first realization of control barrier functions on fixed wing aircraft. And you know, the theory and the theorems actually worked in practice, which is pretty awesome. There are some fun extensions, things like understanding the unification with L1 adaptive control, understanding better when we filter, for example, pilot inputs coming from AI algorithms, how do we couple all those things together to get maximum performance? So with that, I'll maybe take questions if there's time. But again, my deepest thanks for inviting me to this meeting. It was fun to join and talk about this.
I have a question. First of all, thank you for a very interesting presentation and also a combination of interesting results. Back on your CBF theorem, you mentioned something like a Lyapunov kind argument and then necessary and sufficient conditions. So the necessity is a bit difficult unless your inequalities are very accurately determined. And I don't know, this is a question I have, but I found it interesting that you're using your CBF algorithm as an add-on when things are about to be violated. And also the using L1, I think what my instinct from understanding this is that the L1 will probably improve the transients. So it might make it a lot easier for the CBFs to take over and maybe extend. So this is a question and statement, but I will listen to your answer.
Yeah.
But thanks. It was very interesting.
Thank you. These are, by the way, great questions. Let me answer them and I had to skip through a ton of math. That makes me sad that I didn't get to talk about, right? But I'm happy to give more details. But first, let me talk about the theorem itself. So what the theorem says, this is necessary and sufficient, sort of like Lyapunov. And in the same way as Lyapunov, what it says is that if this condition is satisfied for AH, then it implies that your set is forward invariant. It also implies, by the way, that your set is stable. And so this actually, CBFs actually generalize Lyapunov in that they get you stability of a set. And when your set is a point, you recover Lyapunov functions. So CBFs are Lyapunov functions extended, if you'd like, literally, because they take positive and negative values. And that's their difference between Lyapunov. They don't have to be positive definite. To the converse direction, you're right, that is tricky. And what it says is if your set is forward invariant, then there exists a CBF that satisfies this condition. It does not imply, of course, as with Lyapunov, that the CBF you picked is the one that would satisfy that condition necessary and sufficient, right? So as with Lyapunov, it is necessary and sufficient for some CBF, but finding the best CBF is a different story, right? Finding the one that's, and by best, what that means is the least
That's the art of the whole thing.
That's the art of the whole thing. That's the art of the whole thing.
And of course, with a lot of data and experience, I think you can come up with very good ones.
Yeah.
And that would be very interesting.
Yeah. So it turns out that, and, you know, a lot of, these results that were presented here, for example, these CBFs, they're non-trivial to synthesize. We here to get to these CBFs, with this model, we actually have to use backstepping and a bunch of other stuff, right? So you're right. But there is kind of a trick here to synthesize CBFs easily. And that answers your second question. So it turns out we have a lot of papers and a lot of theory about how reduced order models imply safety of the full order dynamics. So let me just spend 1 second, because this is a reduced order model. This is not the true dynamics of the airplane, right? It's an approximation. It's a reduced order model that approximately works. And from this reduced order model, we generate this reference signal that we send to the system. We send that to the flight control computer, right? Now we have a theorem that says that the system is safe for these reduced order models if the signal you're generating can be tracked by the system.
Sure.
And not only that,
Yeah.
but we have a
Yeah.
theorem
Okay.
that says that the goodness of the tracking tells you how conservative that safety is. So what that means is better flight, better tracking algorithms at your flight computer level, taking these filtered actions will mean less conservative behavior. And mathematically, we can show that. And so to answer your question about L1 adaptive, it will make the controller better. And in fact,
Yes.
I've seen evidence of this, which will mean that you will have less conservative, safe behavior, right?
Exactly. We agree. Yeah.
Yeah.
Thank you very
and
much.
so that's a
Thank you.
fantastic question. And that is the art of you tapped right into the art of this that I glossed over with my quick presentation. This is where the math
Appreciate
and the
it.
theory
Thank
all
you.
comes
Yeah.
together.
Yeah.
Yeah, absolutely.
Hey, Eric, this is Kevin
Yep.
Wise. I'm interested in understanding what does the pilot feel in the stick force
Right.
when the CBF is overriding his commands?
Yes, this is a good question. So right now the pilot, this was a limited project, so we didn't get to put we didn't put, let's say, any effort into the HRI aspects of this, right? So right now they're forcing the stick and it's just not doing what they want, right? So it's like if you were driving something, right, you're hitting the gas and it's just not going, right? And so we told the pilot, these are test pilots. These are like, by the way, the pilots are fantastic. I showed a picture of the test pilots flying. They're amazing, right? And so they understood that this was going to happen. And so they were sort of prepared that they were flying. They were sticking the thing and it just wasn't doing what it was, just something was taking over and doing it for them, right? I think in the future, it's important to, how do you convey this to the pilot? Because if they're sticking it one way and the plane's doing something else, that in general would be something you would want to make them aware of, right? So there's visuals you can give, there's vibrations. So on your car right now, right, when you try to turn out of a lane, the lane keeping system will vibrate the steering wheel, let you know that you're trying to do something unsafe. So right now the pilot was just forcing the stick and it wasn't doing what he wanted if it was an unsafe action.
So like when you turn left or turn right, what makes me think about this aspect is in the development of GCAS, which has been around for a long time.
Yep.
Long before CBFs have been around.
Yep.
It basically does the same thing, but how you turn the aircraft and predict what's going to happen in the future ends up being very important policy.
Yep. So
okay.
Two things. Great point. So I was going to even mention GCAS and I didn't. So I'm glad you did. GCAS is a great example. So CBF sort of generalized what GCAS does to all these other scenarios. So every safety limit and safety constraint can now be GCASed with CBFs, right? And so, but I think the other point of that, as you said, and we saw this in the pilot displays and everything, is the GCAS system has a method that's really effective in informing pilots too and everything else. And we'd love to tap into that system and use similar methods to let the pilot know when they're taking an unsafe action, right? And if we're going to override how we're doing that. And as you said, the key is looking forward. And that's what barrier functions do, because this is their key, because they're a dynamic entity, right? That H dot means you're looking at a derivative condition on dynamics. It's giving you future prediction that we can convey to the pilots and let them know what's happening.
Hey, really good work. Thank you.
Thank you.
So Aaron, just a follow-up question. Have you looked at how CBFs can work with learning elements? So for example, right, there's a lot of learning of the system in real time, whether it's a system degraded or you just have a better idea of it, that may change the limits.
Yep.
So have you guys considered how that would work?
Absolutely. Yeah, in many respects. So I'll say there's actually a whole body of work on what are called neuro CBFs now, which we're not doing. That's not from my lab, but was built on the CBF foundations. I do have some papers early on with learning with CBFs where you can kind of filter the learning algorithm. But let me answer another way, the way we've actually done it in my lab and we found really useful. is actually learning the models, because learning the dynamics of the system effectively. And what we've been able to do, and we did this, for example, with drones flying with unmodeled masses hanging from them. So a really good example of very complex dynamics that are not being captured. And what we found is that any learning algorithm can be viewed stochastically. And so we can look at the stochastics associated with the terms you're learning and actually do stochastic barrier functions, meaning we can add additive terms to the barrier function that accounts for the stochastic, the disturbances or the distributions, associated with the learning algorithm and the residuals dynamics that you're learning. And that really, really works effectively in practice too. Meaning once you train this thing, you look at the data, you add these conditions as a CBF, as a stochastic CBF, and we're able to do some really performant things. So I think the broader point is the answer is a fantastic question. And that's just one example. There's lots of ways to integrate learning with CBFs, whether you're filtering a learning controller, applying CBFs to the learning algorithm, meaning the learning process, so that you can avoid bad regions in the learning process, or whether you're using learning within the model dynamics of the CBF, or even learning the CBF itself. So there's lots of opportunities for those intersections, and there's a lot of threads that are really exciting to explore there.
Great, thank you.
Thank you.
Any other questions?
Yeah, hey, this is Mike Atchison. Really great work. You didn't have a chance to get into it. I know it's a short talk. Really interesting stuff. But the look ahead, having knowledge of the barrier rates and the vehicle, the simplified model, it almost seems to me that you're having to plan essentially a trajectory that satisfies all the constraints. And then you're hijacking the aircraft controls to kind of execute that. Am I understanding that correctly, or is it less involved than that?
I would say that it's not so much that it's less involved, but it's different. So what you're talking about is what would happen, for example, if you took like an MPC controller, right? And you took a nominal and then you passed it through a model predictive controller to do a trajectory generation subject to state constraints, right? And you can do that. In fact, we have done that with CBFs. In fact, we've implemented CBFs at an MPC level and passed that to a CBF. And you can do a whole bunch of combinations of that throughout the autonomy stack. But this is different. So we aren't planning trajectories, we're planning inputs, right? Which could be reference signals to a low-level controller. And so what it's really looking is sort of differentially, you're checking in every moment in time whether your current reference signal satisfies the safety constraints. But the way you're looking at the satisfaction is not whether your safety constraint is satisfied at this moment or not, right? But you're looking at the rate of change of how your safety constraint is changing, right? So, I mean, the simplest instantiation is think about it like you have a distance from an obstacle, right? So as long as that distance is positive, you're safe at this moment. But what you really need to factor in on whether you need to brake or not is not your current distance to the obstacle, but how quickly that distance is changing, right?
Yeah.
Because if you're approaching, you might be, 100 feet away, but going 100 meters per second, in which case you probably want to brake, right? You might be 100 feet away and going 1 meter per second, in which case you got some time. So the amount you need to brake is exactly determined by the rate of change of that distance, right? And that's quantified by this inequality that says that basically that rate of change needs to be lower bounded by minus some constant times your distance. And that's that simple math expression, that Lyapunov-like equation dictates how much you need to brake. So we're not slamming on the brakes, but we can gently start to brake far out. Or, and if they keep taking aggressive action, you have to kind of override that more and more. But it's an exchange. It's not a replanning. It's more of a dynamic movement to ensure safety.
Yeah, and that makes sense. And that was kind of my intuition, was that you were essentially just hijacking the controls, locally, so to speak, to make it happen. But you can certainly craft. So what I'm missing is you can certainly craft some scenarios. You have a plane that's a barrier, and let's say you have an intersecting plane that's also a barrier, and you're close to that corner. And while you're approaching one of them, the new actions you're taking are actually making the other situation worse. right?
Yeah.
And now all of a sudden, you either come into an infeasible, scenario or things like that. So in some sense, somehow you're adjusting your CBFs to account for that quote unquote planning part.
So we are in this scenario. So what we're doing in the case of the plane is we're doing some much more intense CBF stuff. This, what I have on this slide, I would call vanilla CBFs. They work really well for most systems. So we need to do something more complicated in the jet scenario, and that does involve these sort of what we call backup policies and implicit safety filtering, which we have papers on this. In fact, they're the ones cited here: Access 2020, IROS 2019, and a bunch of others, where you can include sort of a if you'd like some future knowledge in your corrective actions. And it's not so much a trajectory, like modification per se, but you can include a backup policy. So in the case of the plane, we had a backup policy, which is sort of turn the plane in a specific way, and you can mold that into your CBF. I'm being a little nebulous because the math there gets pretty intense. You are right, though. I want to sort of step back for a second. You are right. Listen, I'm not trying to pretend that CBFs solve all problems universally. So if you have a CBF, meaning you have a bunch of safety conditions, right? Then it's certainly possible, because this is a local condition, you can work yourself into what we call sort of, gridlock conditions, right? Or, deadlocking, or however you want to call it, right? Where you work yourself into a local minimum and in kind of a safe region, but then you have to kind of stop, right? And the only way to avoid those kind of local minimum is to have future knowledge. And so then you have to layer in some future knowledge into the CBF to avoid those deadlock conditions. That requires, again, this is sort of more, I would call this like advanced CBF stuff. There are ways to do it, but it gets more complicated, and there's no free lunch. It's not like there's a universal answer to keep every system safe. And more importantly, again, safety, these are necessary and sufficient, but again, if you put yourself in a scenario where there's nothing you can do to stay safe, meaning you don't have the actuation authority and 10 things are coming at you simultaneously, then there might not be a safe solution, right?
Right.
So I'm not trying to pretend that this solves all problems. You're right. You need to get much more involved if you're going to handle these complicated combinations of CBFs together with input constraints, together with dynamic obstacles and everything else moving in tandem.
Hey, let me ask you one more question in that regard. So the geofencing problem, like if you're aggressively challenging the fence and you need to turn the aircraft, your Dubin's model doesn't have angle of attack. It doesn't have some of the important other state variables of an airplane that you'd have to manage. So what do you do
so we
there?
weren't using the Dubin's per se. We're using slightly more complicated model, right? And Dubin-esque, right?
But still no angle of attack there.
Yeah. So we have one with angle attack as well. It's not shown there. You're right. You have to account for. We have an alpha. We have an alpha term as well that I just didn't include on this slide. But yes, you have to factor in alpha as well. This is reduced without alpha. I knew I'd have some experts. That's why I put the equations, but I should have put all the equations. You have to account for all those things to do this properly, because you have to actually. So what's happening, in this, I mean, it's pretty crazy dynamics that's happening here, in that you see, if you can look at the altitude and the position, right? So as you're doing the geofencing, your altitude, of course, is changing as well, right? This is a combination you're having, just like in the video, right? You have this roll maneuver together with the the geofence roll, which also then, when you're rolling, it drops your altitude. So you have to factor that in as well, so you don't exceed the altitude floor while you're doing the roll, while you're moving away from the geofence. So that you need all those physics. Yeah.
Thank you, Aaron, for the wonderful talk and the excellent Q&As. So,
thank you, Aaron. Right. I also just decided to turn on my video. Thank you very much.
Thank you for inviting me.
Thank you. Thank you, Aaron.
Thank you so much. Thanks, everyone.
Bye-bye.
Take care.
So for our next item on the agenda, we'll have the discussion session. And Irene, if you mind, will you chair this session?
Sure.
And we can slightly extend it to be, say, 2 o'clock, just in counter for the time we didn't have to have.
Yep. So let's do that. And I was going to say, what I want to do during this session, last year, it was something that was actually brought up by the advisory panel, that it would be nice to have some time for discussion, detailed discussion at the end of each day, so we can, the questions would be fresh. Maybe it's a little bit more focused on specific technical challenges, more as a general question or follow up on specific questions. So for bottom line is, let's use the next 25 minutes. I'd like to prioritize the advisory board if they have any questions or comments. And Kevin, I'm going to put you on the spot as the chair to start us off.
Yeah, very good. Thank you. Let's see, really good work and lots of progress since last year. I don't really have any detailed technical questions. I think they may be forthcoming by digging into the slides a little bit more, but yeah, good work. That's pretty much my comments. So I wrote down a few things that I may, I think you've captured them in the chat window too, some of my questions, but.
So we have all the presentations at the link. I put the link in the chat from where you can download all the slides. If you want to download and review them this evening to have the questions tomorrow or for the last day, that's fine. But all the slides are already available from all the speakers.
Today's speakers, right?
All the speakers of 2 days, all the slides are uploaded.
Okay, fantastic. Thank you.
Like one of the questions that I had, like Chu mentioned using verse in, I was just wondering in general, and this was something I put early in the process in the chat when Naira, when you were talking, was, you know, we're pulling together all of these algorithms and now going into flight test. Do we have a process for V&V and what's going to be, what artifacts are going to be generated prior to flight test to show that the system is safe? Because like too often graduate students just keep flying stuff until they crash and then they fix it and then they crash some more. But what are we doing? This is about V&V, right? Of learning enabled components. What's the process for applying verse or whatever other technologies you're going to use to V&V the system before you go to flight?
So Evangelos and Cyan may be able to take that question because Evangelos is going to fly this covariance steering controller, and they are developing it with Christos. And with Cyan, we had this vision-based landing thing that we want so far to be able to test it in simulation. Maybe they two could talk so that we don't talk one after another, all these repeat each other.
Oh yeah, and not that I have to hear an answer right now on that question. So this is something that we can formulate, that you can formulate a more rigorous answer to maybe later. But you know, we would take, we would do, I'll just say functional-based testing. We would do software coverage. You know, these are the kinds of things that would be done to build up artifacts for certification that an algorithm is safe. You know, we would look at disturbances that were simulated. We'd look, you know, we would look at, I'll just say robustness testing. We'd look at command and control into the system. So if you were doing a scenario and now you decided air traffic management decided to command you into some new trajectory. So there could be lots of different inputs into the system that could come, and we would test all of these in kind of a matrix-based test. Yeah, things like that. So I'm just wondering, you know, how do we, what do we say that the final, here's the process of using these technologies that gets us into being able to use learning-based components. Okay, I'll stop there.
Okay, Evangelos, do you want to pick up?
Why it's me again?
Well, because you were discussing this. You were discussing these topics.
Okay. I mean, that's a very hard question, right? Like there are so many modules, so many things, so many different ways.
Yeah.
So I think for the, you know.
Evangelos, we can't hear you. Your voice.
Okay. Can you hear me now?
Yeah.
So for the for the part that has to do with optimization, I think I try to give an answer for my presentation, like you will try to kind of understand input-output relationships. When it comes down to perception, you want to have photorealistic simulators that are very close to reality and do a lot of experiments. And so I think we are coming from different angles here, right? Like Nair is coming with her distributionally robust adaptive control, right? Like to kind of address this question. Like we are coming from the high level planning aspect with covariance steering, and then like the verification of these optimizers. Like you asked that question whether or not this can be verified. So I don't have an answer right now, but what I can say is that like we are working on like from the bottom up, like as little scientists,
Yeah, very good. And that's kind of what I anticipated. Even in some of our programs, we do limited testing about the test point before we go fly it. We don't do full qualification as if we were trying to search something that would be commercially. So I'm not trying to say that you would have to follow that, but I think it would be good to think about here. This is the process that you would recommend be used in the accumulation of all these different things that are in the system. There's a lot of advanced algorithms in here that could easily overwhelm an application like WISC or something of that nature. So I was just curious if the team here has kind of thought about that. Now, so I think this question will get you to think about it, and like, so we would use, 516C. We use on the military side, we follow that. It tells you what kind of artifacts you have to produce, right? We have the DO 178 and other kinds of things for software cert. They tell you what kind of artifacts you have to produce. Not that you have to redefine these standards, but some standard will need to be followed if this technology gets employed. And like, how would it fit into the system to get V&V? That was one question I had. So, I'll stop there and give anybody else on the advisory board a chance to ask something.
Cyan, are you around? Cyan might have had something to add. But it seems Cyan is traveling. So more questions.
Anybody else from the advisory board? Available. If not, Kevin, let me get back a little bit on that for you. So I completely agree, and I hear from some our own side of the house that's dealing more with certification. There's all kinds of things that are going on about certifying autonomous systems and learning systems and all that. Let me ask you this. When you're dealing with something that are new algorithms, right? And you flight testing on vehicles that are, let's be pejorative, attritable vehicles, right? So they're inexpensive, something small, something that you don't want to crash, but it's not a big deal that if it does. How do you go about making sure that you explore the ins and outs of algorithms before you try to put the results into the artifact generation space? Does that make sense?
Oh yeah, definitely. So, just as in a loose way to say some of the things that we do at Boeing, when we want to change an algorithm out, it has a function that it's going to provide, right? So we'll do some kind of change impact analysis on this, and we will assemble teams to try to figure out what could possibly go wrong with this algorithm. Looking at the inputs, looking at the outputs, looking at the internal operation of the algorithm, trying to figure out what testing is required, in the V&V of it. So things of that nature. Not that that's, but this is just kind of like from this program here. You're making great progress. I really like all the stuff that we're seeing here. I'm really glad Aaron showed us the CBF stuff. I really like that too. That was great. So You know, this is a very active area. You know, how do we stitch all these things together? And then what would be the process that we use in doing so? So very good.
So I think it's an excellent question. And just this is my own personal sort of take on this, is that a lot of this is going to be learned in preparation for the demos in May. That's the feeling I got.
think
The other
I
thing
agree.
is,
A lot of great results and very insightful algorithms and approaches have been presented, and this is exactly what should be happening. I think we need more experience and more data for the researchers to hone in to make them more predictable and more accurate and more clearly defined in terms of barriers, in terms like even Aaron mentioned. So all of this will come together at some point. And I think what will probably also be a result will be different sectors of where different classes of algorithms will work, and then they can sort of mesh together to give a much stronger result. But this is down the line. It needs a lot more work, but a lot of progress has been made, and it's very satisfying and impressive. So
if I may add just one thing before Evangelos, you know, I see your hand up. The other thing is I'm very interested in is that you note that there's quite a bit of work that's going on with the photorealistic visualizations and training of algorithms, excuse me, in that environment. And so I'm sure some of you have seen robotics presentations where the claim is that they can now go from literally from simulation to real world without sort of the testing in the real world. And so I'm very curious to see how far that carries in our application. How far can you take the photorealistic simulation and what is that going to look like once you actually go to flight? Where are the, you know, is it done? Is the answer is no, it's not even close. You can only get to, you know, part way, but you still have to go and collect real data. So some of those questions, at least I have, of what's going to show up hopefully by May. But go ahead, Evangelos.
I think just to this point, Irene, I think in robotics, because a lot of these tasks have to do with like interaction with objects and stuff like that, or like in the context of terrestrial autonomy, this interaction is hard to model, and the gap between sim to real is actually bigger. So I would hope that in the context of flight, and when it comes down to vision-based navigation, that the situations that we might be a little bit like we may be dealing with a use case that does not have the challenges of interaction, right? Because you're not really in a continuous. I mean, you have to have models of ground reaction forces and stuff like that, but I think that we will make more progress there than in the context of manipulation or terrestrial agility. That's one comment. And then the other comment is about what Kevin said is that what we have seen in my lab with this deep unfolding methodology is that actually is like it works very well. Like it's surprising how well it works. The fact that you can bring any optimization method down to a functional representation, and then once you have that, once you do your theory and math and show things that you have to show, then you can work on the verification side of things. The part that is difficult and we don't know how to do yet is how to bring the perception in. Like somewhere, if there is another layer that is another, let's say, ML module that does perception and feeds that to the this like unfolded, like optimizer, how this will come in. We have some thoughts, but it's basically work in progress. So I would say like with my the way how I see it right now is like you have a perceptual module that you have to see how you can verify that with a lot of simulators, photorealistic simulators. And then there is the trajectory optimization module, and then there's going to be some tracking L1 adaptive control scheme that. So that's these are the moving parts. But we will find it out. I mean, we will figure it out.
It's like, I think something that would be valuable would be, you know, I'll say a top level architectural view of what's being proposed as a solution space, what DAL or level of rigor these algorithms live in. So some will be LOR1, DAL-A, some of them will be, you know, that was kind of mentioned early on today as well. And, you know, so like perception is that's a really difficult question today to, you know, how we V&V that. We tend not to, like on the KC-46, you know, the autonomous aerial refueling, where the autonomy drives the boom, right? So there, lots of synthetic vision has been used to train the system. Yes. So, but that's not LOR1. So that's you know, all of these things factor into it as well. So what does the architecture look like? What is the level of rigor? And then what does the team propose? Or what is the, if we were to, you know, say snap the chalk line today, this is what we would do. Right. I really like your unfolding discussion. That is, I think, is a common sense way to address the challenge of optimization. So very good. Yep. Thank you.
So if I can just weigh in on this, this is Mike Atchison. I think my my life is coming to an end because I've decided at this point to stand up for autonomous aircraft rather than piloted human ones. So clearly the world is coming to an end. But Kevin, in some ways, what you're asking is unfair, right? And I'll be very specific in what I mean by that. A lot of these algorithms are control centric or things of that nature, and absolutely there's some verification, validation processes for that. But we've started to blend into the decision-making realm, right? And that is, I think the appropriate metric is, does it make better decisions than a human would, right? And that's kind of the metric, right? Perception. I spent a lifetime doing human perception, and let me tell you, we're not really good at it, okay? Trying to find other aircraft. So it's unfair to ask a perception algorithm to be 100% certifiable in perceiving objects, right? The way humans get away with that is because we fuse other information together, right? I don't just rely on vision. I have, you know, a radio, I have, you know, a radar, I do sensor fusion and, you know, intuition and other things that help me to make my best educated guess, right? And so I think what, along the lines of what Evangelos is doing, I think you need to start this work needs to start separating out what are decision processes and what aren't, right? And it's when I'm making smart decisions, that's not going to be 100% certifiable, right? That's not how a human is. You know, if you threw 10 pilots in to the wreck on the Hudson, you know, Sully might have been the only one that landed it successfully, right? Does that mean that, you know, an algorithm that landed 7 out of 10 times when a human can only do it once out of 10 is bad and not certifiable? Heck no. You know, that's the trouble with this, is we have to start to break out what's decision and what's not, right? And that's the challenge, or that's the unfairness, I'll say, of what it seems to me that you're asking for. And I promise this is the one and only time I will stand up for autonomy over human pilots, hopefully in my lifetime.
Oh, no, see, I mean, I can be argumentative about that somewhat because, if we're talking about applications like WISC, which are planning, to start flying in operations just in a couple of years, they're going to have to stand in front of the FAA, and whatever technology they put into their aircraft, they're going to have to guide the FAA through how it was certified. And
Sure.
the FAA is going to have to agree with it, right? So, that's kind of along the lines of my question is, here we have these advanced algorithms. These people are the most intimate with the details of them. They need to help us recommend what is the process that we're going to use. That's kind of where my question was guided, not towards trying to poke anybody in the eye or anything about using autonomy. Yeah.
Yeah, no, of course not, Kevin. And I'm not, I liked your question. I think you're asking the right question. I just want to be careful. If WISC has 7 bird strikes, in the first year, is that a failure? Well, probably not, right? Humans have them all the time. And so I like the idea. We are struggling with a cognitive architecture, right? We know that we need to develop a good one. And so that type of question you're asking of, hey, when we have this, how do we validate it and how do we verify it? That is very valid, and it's a good question. And I know you're not picking on people. I'm just pushing back a little in that we have to just somehow discern between, upper level reasoning and lower level processes, right? That's all I'm trying to get at, because upper level reasoning, we don't have a lock on that. That's all I'm trying to say, right? We're not perfect in that either, and it's probably unrealistic to expect our algorithms to have a 0% failure rate on those upper level decision making processes. That's all I'm trying to say.
Okay, very good. So I have another question that I was going to ask that's not related to this topic. Okay, so I'm going to break. All of the architectures that are being envisioned for operation on, UAM type applications are redundant. And has this team thought about how the implementation across a redundant architecture would work? Not that that's required in this research statement, but I was just wondering if, and the reason why I bring this up is Honeywell was using dynamic inversion on the F-18 HARV, and the way the F-18 signal management logic works is it has 2 sides of the aircraft have independent air data, and that the numbers coming into the software were different enough that it failed in the dynamic inversion control laws and couldn't get past the output signal management plane. And so Honeywell could never fly their algorithms on the HARV because they couldn't V&V in the computers. So the implementation of this in a physical architecture is also an important part of certification as well as the functional architecture. So I was just wondering how do we think that would work? Yeah.
Evangelos, your hot mic.
The honest answer is that we have not thought about it. We of course we are aware about redundancy systems and all of this, right? But I think I personally was so fixating on the certification aspects and the perception that I did not have time to think about how a backup system would look like. But one comment I want to make is that perhaps within the context of this year, we may not be able to, and most likely not be able to verify perception, right? But perhaps there might be a intermediate point, a sweet spot between not having perception at all and having perception, right? And so, for example, right, like you can think about using perception as a way to initialize your autonomy stack. and then go into a mode or, where you have non-vision based perception. Like think about vision-based navigation as a case where you have snapshots, right? So that's very different than like having to stream the entire video, and so then that's a more like specific use case, more specific scenario, right? Where like I have a camera and I see the landing zone, and I want to use that information to, let's say, initialize my autonomous stack, and then like I do the task, and then once in a while I will have the camera to give me like a few snapshots of the. That was for the previous discussion. Sorry, Kevin.
All right, so it is 2 o'clock Central, 3 o'clock Eastern, noon, I guess Pacific. To be cognizant of people's time, I would say let's call it. We'll resume tomorrow morning. It was really excellent discussion and really good questions, Kevin. Hopefully I have captured them in chat. If I have not, let's make sure they're in chat tomorrow, because I think we'll all lose access to it when we log out.
It can be downloaded, the
Sure.
entire recording.
Yes.
Slides can be downloaded separately, the recording of the meeting. Slides and the chat will be also downloaded and saved by us and shared with all of you.
Perfect.
I apologize for my voice. I have been terribly sick, barely talking, holding my cough behind, but I hope I was still able to communicate a good message about the team. Thank you everyone for joining.
Thank you. We'll see you tomorrow morning. Have a good evening.
See you.
Bye.
Thanks. Bye-bye. Bye.